In the earliest chapters of Earth's story, there was no gentle breeze carrying the scent of oceans, no rustling of leaves in the darkness. The planet was young, restless, and still finding its shape beneath a sky that was nothing like the one we know. It was a deep, unbroken expanse, veiled in the faint glow of molten rock and scattered embers from a surface still cooling after the violence of its birth. The sun hung in the distance, smaller in the sky than it seems today. Its light filtered through a haze of gases heavy with carbon dioxide, water vapor, and traces of methane. Nights were darker than the deepest ocean trench, but not entirely still, for the ground pulsed with the slow heartbeat of magma shifting beneath a thin, unstable crust. Above, there was no protective cocoon to soften the sun's temper. Streams of charged particles, the solar wind, flowed constantly from its surface, racing across the emptiness of space at hundreds of kilometers per second. When they met Earth, they found no magnetic shield to turn them aside. The planet's young atmosphere, thin and unguarded, was vulnerable to every gust of this invisible storm. Molecules that might one day have formed the air we breathe were stripped away, lost to the void. Without a barrier, even the promise of water could not be kept for long. The young world stood exposed, every day a test of survival against the relentless breath of its star. The surface was a place of extremes. Vast plains of cooling basalt stretched in every direction, their surfaces still glowing in cracks and fissures where lava welled up from below. Volcanoes rose in jagged silhouettes against the dim light, their eruptions sending plumes into the high, unstable sky. From time to time, fragments of rock from the lingering chaos of the solar system's formation fell through the darkness, striking the surface with brief, violent flashes. These impacts stirred the atmosphere, such as it was, sending waves of heat and gas outward into the empty night. And yet, even in this harsh beginning, there was a strange, fragile beauty. The silence of the night was absolute, broken only by the slow, seismic groans of the planet settling into its new skin. Far above, the stars shone with an unfiltered clarity, untouched by the scattering of a thick atmosphere. Constellations, though unnamed, would have been sharp and unwavering to any eye that might have looked up. The moon had not yet formed, and so the darkness was deeper, the stars more commanding. Without the silvery wash of lunar light, the heavens seemed infinite, their cold brilliance a stark contrast to the molten world below. In this silence lay the seeds of what would come. The molten iron deep within Earth's heart was already moving, though not yet in the great convective currents that would one day give rise to the magnetic shield. For now, the planet endured without armor, its thin atmosphere slowly shaped and reshaped by the sun's fierce energy. Each gust of solar wind was a reminder of the vulnerability of a world without protection, and each rotation under that alien sky was a step toward the moment when the first invisible threads of a magnetic field would begin to weave themselves around the planet. It was a beginning both delicate and dangerous. Without a shield, Earth's story could have ended here, its air and water stripped away until it was as dry and silent as Mars. But deep in its molten heart, the elements of salvation were waiting. The silence of those nights was not the end. It was the pause before the quiet machinery of survival began to stir. The sun, even in its youth, was not the gentle companion we imagine when we picture golden mornings or quiet sunsets. In those ancient days, it burned hotter, spun faster, and flung its energy outward with a force that dwarfed anything we experience today. Streams of charged particles, electrons and protons, born from the sun's roiling surface, poured into space in a ceaseless torrent. This was the solar wind, an invisible tide that never rested, flowing at hundreds of kilometers per second. It was more than just light and warmth. It was a storm without sound, a pressure that could strip the breath from a planet. For Earth, still young and unshielded, this fierce breath was a constant danger. Without a magnetic field to turn these particles aside, the upper atmosphere became a place of erosion. Each collision between a solar particle and a molecule of gas imparted enough energy to send that molecule drifting upward, and if it reached a certain speed, it was lost forever to the void. Hydrogen escaped most easily, light and quick, slipping away into the cold reaches of space. With it went the building blocks of water, the very essence of oceans yet to be born. Over millions of years, such losses could have transformed Earth into a barren world. The solar wind was not constant in strength. At times, the sun's magnetic storms would hurl out even denser, faster clouds of plasma, coronal mass ejections, that swept through space like waves of fire. When they reached Earth, these storms would have battered the atmosphere, compressing it, heating it, and accelerating its loss. Without protection, the planet was like a ship in open water during a hurricane, with no harbor in sight. Beneath this relentless assault, the sky must have carried an unearthly quality. The upper layers of the atmosphere glowed faintly as particles collided with atoms and molecules, releasing energy in brief flashes of light. But unlike the auroras we know, these glows were not confined to the poles. They would have flared and shifted unpredictably, sometimes covering the entire planet in a dim, ghostly shimmer. To an observer, if one had existed, it would have been both beautiful and unsettling, a sign of the invisible war being waged between the sun and the fragile shell of air clinging to Earth. This battle between star and planet was not unique to Earth. Mars, too, felt the sun's breath. But without a molten heart to generate a magnetic shield, Mars lost the fight. Over hundreds of millions of years, its atmosphere thinned to almost nothing, its rivers and lakes evaporating into space. Venus, though still cloaked in thick air, faced its own challenges, relying on other defenses but suffering from an unyielding, searing heat. Earth's path was different, not because the sun was kinder, but because deep within forces were gathering that would change the outcome. The fierce breath of the sun, while dangerous, was also a catalyst. It set the terms of survival, pushing Earth toward the solution it needed. In the swirling metal and rock beneath the crust, heat moved, pressures shifted, and the first hints of a magnetic heartbeat began to emerge. The sun's unending wind demanded resilience, and Earth's molten core was preparing to answer. The day would come when this storm would meet its match, when the charged particles racing from the sun would encounter an invisible wall and be forced to dance harmlessly across the sky. But for now, the breath of the sun was still an untamed force, shaping the destiny of the planet with every passing moment. In the modern world, we think of sunlight as a blessing. It nurtures the forests, warms the oceans, and gives life its rhythm. But on the newborn Earth, light was a double-edged gift. The sun's rays brought not only heat and brightness but also invisible blades of energy, ultraviolet radiation and streams of high-energy particles that could tear apart the fragile chemistry of life before it had even begun. The young sun was far more restless than it is today. Its surface boiled with activity, its magnetic fields twisted and snapped, unleashing flares that hurled vast bursts of energy into space. These flares were not rare, fleeting events. They were woven into the fabric of the sun's daily life, each one sending dangerous radiation outward in every direction. Earth, still without its protective magnetic cocoon, bore the brunt of these assaults. Ultraviolet light, unchecked, penetrated the thin atmosphere with ease. On the ground, it would have been lethal to any delicate molecules that might have tried to assemble into the building blocks of life. DNA, if it had existed in that time, would have unraveled in seconds beneath such unfiltered light. Water near the surface of the land would have steamed and split, its hydrogen escaping into space, leaving oxygen to react with the minerals of the crust. Even the oceans, if they had begun to gather, would have been shallow, warm, and unprotected from the sun's glare. But this threat was not a silent one. It shaped the early chemistry of the planet in ways both destructive and creative. Ultraviolet light, for all its danger, also carried the energy needed to spark certain reactions. Simple molecules floating in the atmosphere or dissolved in pools of water could be broken apart and rearranged, forming new compounds, some of which may have been precursors to the chemistry of life. It was a paradox. The same light that could destroy also had the power to create. Still, the balance was precarious. Too much exposure, and fragile chains of molecules would be shattered faster than they could form. Too little, and the reactions that built complexity would stall. Without some kind of protection, the scales tipped dangerously toward destruction. The young Earth needed a filter, a way to block the worst of the sun's violence, while allowing enough light for life's first experiments to continue. The answer would not come from the atmosphere alone. While certain gases could absorb some ultraviolet rays, they were no match for the deeper, more penetrating forms of radiation. The planet required a shield that worked at a fundamental level, intercepting the charged particles before they could even touch the air. That shield would have to be vast, reaching far into space, bending and guiding the solar wind so that only a softened, tamed version could pass through. In time, Earth would forge that shield in the furnace of its own heart. But in these early days, the threat from above was a constant reminder of the planet's vulnerability. Every sunrise brought both hope and peril. Every shaft of light carried the promise of life and the danger of death. It was a lesson written into the very history of the world. Light is not simply warmth. It is power, and power must be tamed before it can be trusted. In the quiet hours after Earth's violent beginnings, a tenuous veil began to form around the planet. It was not yet the rich, life-sustaining air we know today. Instead, it was a patchwork of gases, drifting and shifting like a mist that could vanish at the faintest disturbance. This first atmosphere was born from two main sources: the ancient breath of the planet's own interior, and the gifts, and sometimes curses, delivered by objects from the far reaches of the solar system. Volcanoes, countless and restless, punctured the crust with fiery mouths. From their depths came plumes of carbon dioxide, water vapor, nitrogen, and traces of methane, each molecule rising into the sky like a note in an unfinished symphony. The air was heavy with the scent of minerals and the sharp tang of sulfur. There was no oxygen yet, no blue skies or gentle breezes, only the raw exhalation of a world still cooling. Beyond Earth, comets wandered the young solar system like messengers from a colder realm. Some carried icy cargo that, upon striking the planet, would vaporize instantly, releasing both water and exotic gases into the thin envelope above. Asteroids, too, joined in this chaotic exchange, their impacts shaking the surface and sending dust and vapor swirling upward. These arrivals could enrich the atmosphere but could just as easily strip it away in a single catastrophic blow. Yet for all these contributions, the atmosphere remained fragile. Without a magnetic shield, the solar wind brushed against it constantly, like an unseen tide pulling at its edges. Hydrogen, the lightest and most elusive gas, escaped most easily, drifting away into the darkness of space. Over time, this loss chipped away at the planet's ability to hold onto water in its vapor form, leaving a delicate balance between replenishment and erosion. The color of the sky under this first atmosphere would have been strange to our eyes. Instead of the clear blue we know, it might have been hazy and muted, its tones shaped by the scattering of sunlight through thick, carbon-rich air. On the ground, shadows would have fallen softly, blurred by the ever-present mist of particles and vapors. Temperatures would have swung wildly between scorching days and frigid nights, the thin air unable to hold the sun's warmth for long. Still, even in its frailty, this atmosphere was more than an ornament. It softened the blow of smaller meteors, shielded the surface from some ultraviolet light, and held enough heat to keep liquid water possible in certain places. It was a beginning, a promise that the planet could, in time, nurture something more. But without further protection, it remained vulnerable to the sun's will. A single surge of solar wind could strip away years of volcanic effort, scattering molecules into the void. Deep within Earth's molten heart, a solution was slowly taking shape. Heat, pressure, and motion were beginning to organize themselves into patterns that could sustain something greater than a fleeting mist. Soon, the planet would no longer have to endure the constant theft of its breath. It would build a shield strong enough to hold the air close, to keep the warmth in and the dangers out. But for now, Earth inhaled and exhaled in short, shallow breaths, its atmosphere as delicate and temporary as the morning fog. Far across the solar system's expanse, Mars drifts in its quiet orbit, a small, rust-colored world with a history written in dried riverbeds and the ghosts of ancient lakes. Today, Its thin atmosphere offers little comfort from the cold and almost no protection from the sun's constant wind. But long ago, Mars was different. Its surface bore the signs of flowing water, its valleys carved by streams, its basins filled with lakes that may have glimmered under a gentler sky. For a time, it held the ingredients for life: liquid water, a thicker atmosphere, and a climate that might have been mild enough to nurture it. Then something changed. The magnetic field that had once wrapped Mars in a protective cocoon began to falter. Perhaps its smaller size meant it cooled too quickly, the molten dynamo in its core slowing and then stopping. Without that magnetic shield, the solar wind swept in unhindered, striking the upper atmosphere and stealing it away molecule by molecule. Over millions of years, the air thinned, the pressure dropped, and the water that had once moved freely on the surface vanished into space or froze beneath the ground. The planet's warmth bled away, leaving it locked in a deep, unyielding chill. Mars became a warning, though no one was there to hear it. It showed what happens when a world loses its heart's motion, when the invisible barrier between star and surface collapses. Rivers that had run for thousands of years dried into dusty channels. Clouds disappeared from the sky. Any living things that might have taken hold were left exposed to radiation, struggling in an environment that grew more hostile with each passing century. For Earth, this fate was not an impossibility. Without a functioning magnetic field, our planet could have followed Mars into stillness and silence. The sun would have done its slow work, stripping away our air, erasing the seas, and leaving a barren shell behind. The difference was that deep beneath Earth's crust, the core was larger, hotter, and more dynamic than Mars's had ever been. This gave our planet a second chance, a way to build a defense that could endure for billions of years. Still, the thought lingers. How many worlds once alive now drift lifeless, their skies gone, their surfaces frozen under the same sun that warms us? The solar system carries their stories in craters and rock formations, each a reminder that survival is not simply a matter of having the right ingredients. It is about holding onto them, protecting them from the forces that would take them away. Mars continues its lonely orbit, a silent neighbor that once might have been a sibling in vitality. Now it stands as a mirror of what could have been Earth's destiny, had our planet's molten heart cooled too soon. Every gust of solar wind that brushes against Earth's magnetic field today is a continuation of the same battle Mars once fought and lost. Our shield still holds, but the story of Mars ensures we remember what happens when it fails. Beneath the continents and oceans, deeper than the deepest trench, Earth hides a heart unlike any other, a core of metal, restless and alive. It is not the still, solid heart one might imagine, but a layered realm where heat, pressure, and motion are locked in a constant, intricate dance. At its center lies the inner core, a sphere of solid iron and nickel, compressed so tightly that it remains solid despite temperatures hotter than the surface of the sun. Around it swirls the outer core, a vast ocean of molten metal that churns and flows under forces both ancient and unyielding. This moving heart is powered by heat left over from Earth's violent birth, the slow decay of radioactive elements, and the crystallization of the inner core itself. As the inner core grows, iron solidifies and releases lighter elements into the outer core. These lighter materials rise, creating convection currents in the molten metal. Combined with the planet's steady rotation, these currents twist and spiral, generating electric currents on a colossal scale. From these electric currents comes an invisible yet essential force: the magnetic field. It is this restless motion, this ceaseless stirring of molten iron, that transforms Earth into a giant dynamo. Without the movement, the magnetic field would vanish, just as it did on Mars when its core fell still. And yet, for all its importance, the outer core is beyond our reach. No human will ever walk there, for the crushing pressure and searing heat would destroy any vessel long before it arrived. Everything we know about this hidden ocean comes from indirect evidence. The way seismic waves bend and slow as they pass through it, the variations in Earth's gravity, and the changes in the magnetic field we measure at the surface. It is strange to think that the safety of our skies, the stability of our climate, and the preservation of our seas all depend on a process taking place thousands of kilometers below our feet. The outer core's slow, powerful churn is as vital to life as sunlight or water. Without it, the shield that turns away the sun's dangerous wind would dissolve, and the delicate balance of our atmosphere would unravel. The movement of the core is not constant in strength. It pulses and shifts over long stretches of time, sometimes altering the shape of the magnetic field or causing its poles to wander. But it has never stopped completely, not in over 4 billion years. Its endurance is the reason our world still breathes beneath a protective sky. The Earth's heart is not a quiet thing. It is a deep, rolling thunder, a song without sound that has played since the planet's earliest days. When you stand on the surface, feeling nothing but the cool touch of the wind, it is easy to forget that such a storm of molten metal turns far below. Yet every compass needle, every aurora, every breath of air you take is linked to that unseen motion. It is the foundation upon which all life rests, a living engine that works in darkness, asking for nothing in return. Deep within the planet, the movements of molten metal had been building toward a threshold. For millions of years, the outer core's churning was chaotic, driven by the uneven release of heat from the mantle above and the gradual cooling of the planet as a whole. But as the inner core began to grow, something remarkable happened. The flows of molten iron found rhythm. Heat, buoyancy, and the planet's steady rotation combined in just the right way to create vast, spiraling currents, patterns that could endure for millennia. In this moment, the geodynamo was born. It is not a machine in the sense of gears and pistons, but the principle is the same. Moving conductors, in this case, rivers of molten metal, generate electricity. And in Earth's vast, hidden generator, the electric currents were so immense that they created a magnetic field strong enough to reach far beyond the surface, out into space. The transformation was profound but invisible. There was no sound, no flash of light to announce that Earth now possessed a magnetic shield. Yet the effects began immediately. The field extended outward in all directions, shaping itself into a teardrop-like bubble around the planet. This magnetosphere would become the guardian of the atmosphere, deflecting most of the sun's charged particles so that they flowed harmlessly around the planet instead of crashing directly into it. Without knowing it, Earth had crossed a line between vulnerability and resilience. For the first time, the solar wind met resistance. Charged particles, once free to strip away the planet's breath, now curved and spiraled along invisible lines of force. Some were guided toward the poles, where they would create fleeting veils of light in the upper atmosphere. The first auroras, flickering like a signature written across the night sky. The geodynamo was not a fragile creation. It was rooted in the deep, enduring motion of the core, a process fueled by both the slow cooling of the planet and the growth of the inner core. As long as the outer core flowed, the magnetic field would persist. It could shift, weaken, or even reverse its polarity over time, but it would remain, a silent guardian powered by the restless depths. What makes this awakening extraordinary is that it happened without intention, without design. The same physical laws that guided the formation of stars and the orbits of planets also shaped the conditions inside Earth, ensuring that this shield would rise when it was needed most. It is a reminder that protection does not always come from deliberate action. Sometimes it emerges from the natural unfolding of the world itself. Above the surface, life had not yet begun, but the stage was being prepared. Without this shield, the fragile molecules that would one day form living cells might never have survived long enough to replicate. The geodynamo's birth was, in a sense, the first quiet step toward the possibility of forests, oceans, and human voices speaking under a blue sky. In the deep silence of the core, the heartbeat of the planet had begun, and with it the promise of a future. The magnetic field that rose from Earth's core did not spread outward as a featureless haze. It took on form, an architecture sculpted by the flow of molten metal and the rotation of the planet. Imagine invisible lines looping from the southern hemisphere into space, curving high above the atmosphere, then diving back down into the northern hemisphere. These lines of force, paths along which magnetic influence travels, created a framework that extended far beyond the reach of the clouds, into the emptiness between worlds. To human eyes, they are imperceptible. No shimmer marks their boundaries. No texture reveals their shape. Yet their presence can be felt in the way a compass needle aligns itself, or in the way charged particles are guided, captured, and moved along their curves. The magnetic field is not uniform. It bends and twists in response to the solar wind pressing against it, creating a protective bubble whose day side is compressed toward Earth, while the night side stretches into a long, trailing tail. These lines of force are not merely abstract patterns. They are conduits, highways along which energy and matter travel. Particles from the sun that manage to breach the outer boundary of the magnetosphere find themselves caught in these loops, spiraling along them toward the polar regions. Here, in the thin upper atmosphere, they collide with oxygen and nitrogen, releasing energy in bursts of color. This is how the ribbons of light auroras are born. Long before any living creature could look up and see them, these auroras flickered over the poles, silent proof that the shield was working. Each shimmering veil was the end of a journey, the point where a particle's violent path through space transformed into a dance of light. To an observer, had one existed, it would have seemed like the heavens themselves were breathing, the night sky shifting and swaying in slow, hypnotic waves. The geometry of the magnetic field is always in motion. The lines of force bend under the pressure of solar storms, then relax when the skies grow calmer. They can reconnect, snap, and reform, releasing bursts of energy that ripple through the magnetosphere. Even in the quietest times, there is movement, a ceaseless adjustment to the sun's changing moods. What is remarkable is how these invisible lines create a structure of such immense scale and yet remain entirely intangible. They hold no weight, cast no shadow, and yet they shape the fate of a planet. Without them, the solar wind would carve directly into the atmosphere, and the surface would be left exposed to radiation and the slow theft of air. With them, Earth is able to keep its breath, its water, and its capacity for life. Far above the poles, where the lines converge, the auroras still glow in our own time, just as they did in those early days. They are not merely beautiful. They are messages from the shield, a reminder that the same lines of force that shape the ribbons of light also hold back the storms of the sun. And though we cannot see the field itself, we live every day within its embrace, walking across the surface of a world wrapped in threads of invisible strength. For most of its life, Earth's magnetic field has been an unseen presence, silent, invisible, and constant. But in certain places, at certain times, the shield reveals itself in a spectacle of light so mesmerizing that even without knowing the science, one could feel its significance. These are the auroras, the luminous veils that ripple across the skies near the poles, where the magnetic field lines guide charged particles from the sun into the upper atmosphere. When those particles, moving at tremendous speeds, collide with atoms of oxygen and nitrogen high above the ground, they pass on some of their energy. The atoms absorb it, then release it again as light. Oxygen glows green or red, depending on the altitude. Nitrogen adds shades of purple, violet, or blue. Together they weave patterns that shift and flow, painting the night in colors that seem almost alive. The movement is slow and graceful, like curtains stirred by an invisible breeze. Yet behind that elegance is a process of immense power. In those early days, before any eyes could witness them, auroras would have appeared far more frequently and possibly far brighter than they do today. The young sun's solar wind was stronger, sending more particles rushing toward Earth. Each impact with the upper atmosphere would have set the polar skies alight, not as a rare event, but as a common rhythm of the planet's interaction with its star. The lights would have been a constant reminder, had there been anyone to see, that the shield was not just a static wall, but a living system, absorbing, redirecting, and transforming energy from space. Today, when we watch an aurora, we are looking directly at the magnetic field's work made visible. Every shifting ribbon marks a place where the shield has taken a blow from the solar wind and softened it into beauty. What could have been a destructive surge of radiation becomes a dance of light, harmless to those below. The aurora is, in a sense, the shield's signature, its way of announcing, "I am here and I am working." The spectacle has inspired countless myths and legends. To the Inuit of the Arctic, the lights were the spirits of the dead playing a game in the sky. To the Sami people of Scandinavia, they were believed to be the energy of souls, a phenomenon to be treated with respect. Across cultures and centuries, people have looked up at the aurora and felt that it was something beyond ordinary weather, a sign of a connection between the earth and the heavens. And in a way, they were right. The aurora is the meeting point of solar and terrestrial forces, the visible handshake between star and planet. Even now, as scientists study them with satellites and ground-based cameras, auroras retain their sense of mystery. They remind us that the shield is not a static barrier, but a dynamic, breathing system. The lights shimmer, fade, and return, each display shaped by the shifting winds of the sun and the deep, molten movements within the Earth's core. To see them is to glimpse the boundary of our world, a luminous frontier where danger becomes beauty, and where the silent work of the planet's heart is written across the night sky. For all its seeming stability, Earth's magnetic field is not fixed in one unchanging shape. Over the course of millions of years, it has a habit of doing something strange, something that might seem chaotic at first glance. It flips. The north and south magnetic poles trade places, a process known as a magnetic reversal. To those of us who rely on compasses, such an event would be bewildering. But to the planet, it is simply part of the magnetic field's long, slow breathing. The cause of these reversals lies deep in the outer core, in the restless flow of molten iron. The geodynamo that powers the field is not a perfectly ordered machine. It is a turbulent, ever-changing ocean of metal, where currents shift and spiral in unpredictable ways. Over time, these changes can weaken the overall structure of the magnetic field, allowing smaller regions of opposite polarity to emerge. When these regions grow and spread, they can overwhelm the existing pattern, causing the poles to swap. From the surface, a reversal is not sudden. It unfolds over thousands, sometimes tens of thousands of years. During this time, the magnetic field weakens, its strength dropping to a fraction of its usual power. The shield still functions, but more solar and cosmic radiation can slip through, especially at lower latitudes. Auroras might become common far from the poles, and the navigation of animals that use Earth's magnetic cues, birds, turtles, even certain bacteria, could be disrupted. The rocks remember these events even when we cannot. As lava cools and solidifies, the magnetic minerals within it align themselves with the direction of the magnetic field at that moment. In ancient lava flows, scientists have found layers where this alignment points not northward but southward, evidence of past flips locked into the stone. By studying these records, we have learned that reversals have happened many times with no strict timetable, sometimes separated by millions of years, sometimes by less than 100,000. It is tempting to imagine the world during such a time. Skies more frequently lit with auroras, compasses spinning with uncertainty, the invisible shield still holding but shifting its pattern like a vast, unseen tide. To early humans, had they lived through one, the changes might have been a source of both awe and confusion. Yet life has endured every reversal. The field never vanishes completely. It weakens, reshapes, and then strengthens again in its new configuration. In this way, magnetic reversals remind us that Earth's shield is alive, not a static wall but a dynamic force shaped by the flows of the planet's molten heart. It adapts, reorganizes, and renews itself, ensuring that the sun's fierce wind cannot strip away our air and water. The flips may seem like instability, but they are, in truth, part of the resilience of the system. A slow, steady proof that change does not always mean loss. Every breath you take is a quiet miracle of planetary protection. The oxygen that fills your lungs, the nitrogen that cushions each inhale, the delicate balance of gases that makes life possible. All of it is here because Earth has learned to hold onto its air. Without the magnetic shield, this atmosphere would be far more fragile, vulnerable to the sun's steady erosion. Over time, even the most abundant gases could be stripped away, leaving behind a barren world, cold and silent like Mars. The magnetic field defends the atmosphere in ways both direct and subtle. Directly, it stands as a barrier against the charged particles of the solar wind, guiding them around the planet so they never collide with the air in full force. Without that deflection, Each gust of the solar wind would be like a hand brushing over the atmosphere, tugging at its molecules, carrying them off into space. More subtly, the field preserves the conditions that keep our air bound to the planet. It maintains the stability of the upper atmosphere, shielding it from the constant battering that could heat it, expand it, and make its gases more likely to escape. The lighter the gas, the easier it is for it to drift away forever. Hydrogen, the key ingredient of water, is the most vulnerable. With each molecule lost, the potential for oceans diminishes. This defense is not perfect. Earth has always lost some atmosphere to space. But with the shield in place, the rate of loss is slow enough that the balance remains. Over billions of years, that stability has given lifetime to emerge and evolve. The air we breathe today is the product of countless interactions between the planet's geology, its oceans, its living organisms, and the magnetic field that keeps these systems from being undone by the sun's breath. It is a relationship so constant that we rarely notice it. We step outside and trust the air will be there, unchanged and ready. We climb mountains, sail across seas, and explore deserts without worrying that the sky above might thin or vanish. This quiet certainty exists because, deep within Earth's molten core, a churning ocean of iron and nickel never rests. Its movement, unseen and silent, powers the shield that lets our planet keep its breath. Imagine standing under the stars, knowing that every molecule of air around you is held in place by forces you cannot see. The wind on your face is the movement of gases that would be lost to space without the shield. The warmth you feel is trapped in part because the air can linger, wrapping the planet like a blanket. Our atmosphere is not simply a backdrop to life. It is the stage on which all life plays its part. And the magnetic field, born of the Earth's deep and ancient heart, is the unseen stagehand ensuring that the play continues. If air is the breath of the planet, water is its lifeblood. Rivers that weave through valleys, rain that nourishes the land, oceans that cradle entire ecosystems. These are the elements that make Earth unlike any other known world. Yet water, like air, is vulnerable. The molecules that make it, two hydrogen atoms bound to one of oxygen, are delicate in the face of the sun's constant wind. And without the protection of the magnetic field, the story of water on Earth could have been tragically short. Hydrogen, being the lightest element, is quick to escape into space. In the upper atmosphere, where the sun's energy is strongest, it can be heated and accelerated to speeds that carry it beyond Earth's gravitational reach. Once hydrogen is gone, it takes with it the possibility of water. On Mars, this slow escape played out over millions of years, turning lakes and rivers into dusty scars, leaving only ice locked deep below the surface. Earth's magnetic field interrupts that fate. By deflecting the charged particles of the solar wind, it prevents them from colliding directly with the upper atmosphere, where they could break apart water molecules and sweep their hydrogen into space. The shield also reduces the overall heating of the upper atmosphere, making it harder for hydrogen to reach the speeds needed to escape. In this way, the magnetic field is not just a guardian of air, it is a quiet custodian of the oceans themselves. This protection has been in place for billions of years, giving water the time it needed to cycle endlessly between sea, sky, and land. Rain falls, rivers flow, ice melts, clouds gather, an eternal motion that sustains life in all its forms. Without the shield, this cycle would have been disrupted, its reservoirs drained into the void long before forests, coral reefs, or human civilizations could ever take shape. Even in the planet's most ancient days, when water first pooled on its surface, the presence of a magnetic field would have tipped the balance toward retention. Each droplet that survived the sun's scrutiny was a building block for oceans, lakes, and rain-fed streams. Over time, the abundance of water became one of Earth's defining features, a constant presence in the stories of life and landscape. It is easy to take this for granted. We walk along beaches, listen to the crash of waves, drink from rivers, and rarely think of the invisible shield that makes such experiences possible. But every tide, every drop that falls from the sky, exists in part because Earth's heart keeps turning, because the molten metal below our feet never stops moving. The magnetic field is not just a protector, it is a preserver of memory, keeping the oceans as a link between the Earth we inherited and the Earth we will leave behind. Long before forests swayed in the wind or creatures roamed across continents, the first stirrings of life began in the most unassuming places. Microscopic forms drifting in water, clinging to rocks, or hiding in the shadows of the deep. These early organisms were fragile, their chemistry easily undone by the sun's unfiltered radiation. Without protection, their delicate molecules, especially the chains of nucleic acids that carried the instructions for life, could have been shattered as quickly as they formed. The magnetic field changed that. By deflecting the charged particles of the solar wind and limiting the most dangerous radiation from reaching the surface, it gave Earth something rare in the cosmos: stable spaces where life could take root. In these sheltered pockets, chemical reactions could proceed without being constantly broken apart. Molecules had the time to copy themselves, to evolve complexity, and to experiment with the endless variations that would eventually give rise to cells. In the oceans, where water already offered some shielding from radiation, the magnetic field's contribution was especially profound. With the worst of the solar wind held at bay, shallow waters became nurseries for photosynthetic organisms, tiny architects that would one day flood the planet with oxygen. Near hydrothermal vents, where mineral-rich water surged upward from the deep, early microbial communities could flourish without the constant threat of atmospheric erosion or radiation sterilization. These first life forms may have been so small they were invisible to the naked eye, yet they were the foundation for everything that followed. The shield above did not shape their chemistry directly, but it created the conditions in which they could persist through generations, slowly adapting to the planet's shifting environments. Over vast stretches of time, the line between survival and extinction often depended on the steadiness of the magnetic field's protection. Without it, Earth might have resembled other barren worlds where the sun's energy stripped away both atmosphere and potential. With it, the planet became not only habitable but hospitable, a place where life was not just possible but increasingly likely. Every step in life's early story, from the first replicating molecules to the first true cells, unfolded beneath the quiet watch of this unseen guardian. Even now, billions of years later, the descendants of those early organisms carry within their structures the legacy of that ancient safety. The genetic codes that define all living things were written in an era when the magnetic field's protection allowed them to endure long enough to be refined and perfected. Our own existence is a continuation of that story, an echo of the first shelter Earth ever offered to life. From the moment the geodynamo awoke, Earth and the sun became locked in a delicate, ongoing exchange. A dance of energy and force that has lasted for billions of years. The sun, with its boundless power, sends streams of charged particles racing outward in all directions. Earth, in turn, bends and shapes those streams, guiding them around its magnetic field like a dancer turning aside a partner's momentum. Neither is still and neither entirely controls the other. It is a relationship defined by motion and adaptation. The sun's output is not constant. It pulses with an 11-year cycle of activity, sometimes calm and quiet, sometimes restless with solar flares and coronal mass ejections. In its younger years, these cycles were far more intense, the winds stronger, the bursts of plasma more frequent. Earth's magnetic field has had to adapt to each of these moods, flexing and stretching, sometimes pushed to its limits during powerful storms. When a major solar storm strikes, the magnetosphere ripples and compresses. Lines of magnetic force twist and snap, releasing energy that races toward the poles, igniting auroras brighter and more widespread than usual. In the early ages of Earth, such storms must have been common, filling the polar skies with luminous veils for days at a time. Each display was more than beauty. It was a sign that the shield was holding, absorbing the impact and turning violence into light. But this dance is not entirely one-sided. The sun shapes Earth's field, and Earth's field, in turn, influences the space around the planet. It creates a safe zone where charged particles are trapped in two great belts encircling the globe, the Van Allen belts. While dangerous to spacecraft and unprotected astronauts, these regions are also part of the planet's defense, catching particles before they can descend toward the atmosphere. Over geological time, both partners in this dance have changed. The sun has grown slightly brighter, its rotation slowed, its winds gentler than in its youth. Earth's core has cooled just enough to expand the solid inner core, strengthening the convection in the outer core and, for now, sustaining a robust magnetic field. This balance is not permanent, it will evolve as all things do, but for billions of years it has been enough to keep the planet habitable. Standing under the night sky today, it is easy to forget that this dance is happening at all. The magnetosphere's movements are silent, invisible, unfolding far above and far below us. Yet without it, the story of life would be vastly different. Every rotation of the Earth, every burst from the sun, every shimmering aurora is a step in this long, slow choreography. A reminder that survival is not just about enduring, but about moving in harmony with the forces that shape our world. For all its strength, Earth's magnetic field is not unshakable. There have been times, scattered across the planet's long history, when the shield weakened, thinning to a fraction of its usual power. These were not sudden collapses, but slow changes, unfolding over thousands of years as the restless flows in the outer core shifted and reorganized. Yet even gradual changes can have profound effects, for the magnetosphere is our first and most vital line of defense. When the field weakens, more charged particles from the sun slip through its outer boundaries. The magnetosphere shrinks, compressed closer to the planet by the pressure of the solar wind. In the upper atmosphere, energy from these particles can strip away gases more quickly, heating the thin air and nudging its lightest molecules toward escape. Auroras, normally confined to the poles, bloom across the skies at lower latitudes, casting shimmering curtains of green and red above places unaccustomed to such light. These intervals of weakness are often linked to magnetic reversals, when the poles trade places, or to smaller, partial shifts known as excursions. In each case, the field does not vanish entirely. It is too deeply rooted in the molten core for that, but its protection is diminished. If such a period coincided with a particularly violent phase of solar activity, the effects could be felt in ways both subtle and dramatic. For life on Earth, these episodes have not been fatal. The atmosphere, even when more exposed, remains thick enough to shield the surface from most harmful radiation. But there are signs that in past ages, periods of weakened magnetism may have coincided with shifts in climate or with stress on certain ecosystems. The loss of some atmospheric gases, especially over long spans of time, could alter the planet's balance in ways that ripple outward through the living world. To modern humans, the implications are different but still significant. A weak magnetic field would make our satellites more vulnerable to radiation damage, interfere with radio communications, and increase the risk to astronauts traveling beyond the safety of low Earth orbit. Our technological civilization depends on systems that are, in their own way, as delicate as the earliest life forms were to the sun's glare. Yet history shows that the shield always recovers. The same deep forces that cause its momentary faltering also drive its renewal. The flows in the outer core reorganize, the magnetic field strengthens, and the invisible wall against the solar wind rises again. In this resilience lies a quiet reassurance. The shield may bend, but it does not easily break. It is a reminder, too, of the fragile balance we inhabit. Our protection depends on a process hidden far below, in a place we can never visit, sustained by heat and motion that have endured for billions of years. When the shield falters, we glimpse the truth that life on Earth is always in dialogue with the deep, molten heart of the planet, and that this conversation has no pause, only changes in tone. Far beneath the continents, in a darkness that no light has ever touched, Earth's core turns and flows with a rhythm older than the oceans. This movement is not perfectly steady. It pulses, shifts, and changes over time, much like a living heart adjusting to the needs of the body it sustains. Scientists call this variability secular variation, the slow drift and fluctuation of the magnetic field over years, centuries, and millennia. To imagine it is to picture an invisible tide, rising and falling on a timescale so vast that a single human life barely registers its motion. The magnetic heartbeat is not measured in sound, but in the subtle movement of the field's poles, in the way its strength grows and wanes across the globe. The North Magnetic Pole, for example, does not sit still. It drifts across the Arctic at tens of kilometers a year, tracing a wandering path dictated by the balance of forces deep within the core. These changes ripple outward, altering navigation patterns for migratory animals and requiring updates to the maps and systems humans rely on. In the core itself, the heartbeat comes from the competing motions of molten iron. Some flows strengthen the field, others weaken it, and their interplay is never entirely predictable. At times, vast regions of opposite polarity appear under the surface, slowly rising until they alter the field above. At other times, the motion of the core aligns in a way that reinforces the field's stability, allowing the shield to grow stronger and more symmetrical. For all its complexity, the heartbeat is essential to the planet's long-term resilience. It is the reason the magnetic field can renew itself after reversals, why it can adapt to the sun's changing moods, and why the shield has lasted for billions of years. Without these deep, shifting currents, the dynamo would stall, the field would fade, and the atmosphere would begin its slow retreat into space. This constant adjustment is also why the magnetic field is never exactly the same from one moment to the next. If you could see its shape, it would look like a living thing, flexing, breathing, and stretching, its lines of force swaying in response to the interplay of inner and outer forces. From our perspective on the surface, it seems eternal, but in truth it is always in motion, responding to the silent demands of the core and the distant pull of the sun. The heartbeat of the Earth is a reminder that stability is often the product of constant change. Our safety does not come from an unchanging shield but from one that is dynamic, adaptable, and alive in its own way. Every compass needle, every aurora, every gust of wind that still carries the scent of the sea is part of a story written by this deep, hidden pulse. As long as the heart of the Earth keeps beating, the shield will hold, and life will have the space it needs to endure. Among all the worlds we know, Earth alone wears a shield born of a molten heart. Other planets have magnetic fields, but none have combined strength, stability, and endurance in quite the same way. Mercury holds a faint echo of such protection, but it is weak and uneven. Jupiter and Saturn possess fields far stronger than Earth's, yet they are giants of gas and storm, worlds where the concept of surface does not exist in any form we could stand upon. Mars once had a magnetic shield, but it faded long ago. Venus, similar in size to Earth, spins too slowly for a dynamo to thrive. In this vast planetary family, Earth's magnetic field is not simply an accident. It is a rare alignment of conditions. Our planet's size is part of the secret, large enough to retain heat for billions of years, yet small enough for the core's slow cooling to create a solid inner heart. Earth's proportions allow the geodynamo to run continuously. Rotation plays its part as well. The daily spin twists and organizes the convection in the outer core into coherent patterns, turning random motion into ordered currents capable of generating a powerful field. Add to this the composition of the core, rich in iron and nickel with lighter elements to fuel buoyant rise, and the recipe for a lasting shield emerges. It is a gift measured not in years but in epochs. Through ice ages and warm periods, through the rise and fall of continents, the field has remained. It has wandered, reversed, and pulsed, but it has never left Earth without some form of protection. This constancy has allowed the atmosphere to persist and the oceans to stay full, giving life an unbroken window of time in which to grow from microbes to forests, from single cells to civilizations. Without this gift, the trajectory of life would have been entirely different, if life had managed to exist at all. A planet without a shield is a place where the sun is both a giver and a thief, bestowing light but stealing the very elements that sustain living systems. The existence of our magnetic field means that the sunlight which reaches us can nurture rather than destroy, and that the chemistry of life can play out on the surface rather than hide forever in the depths. We tend to think of gifts as intentional offerings, but this one was shaped by chance and by the unbending laws of physics. No hand placed it here, yet its value is immeasurable. It is the quiet foundation beneath every mountain, every river, every living thing that breathes beneath the sky. Other worlds may have their own wonders, but here on Earth, the shield is ours alone. A signature of the planet's deep vitality, and a reminder that we live on a rare and fortunate world. On certain nights, far from the noise of cities, the shield shows its face. Curtains of green, violet, and crimson sway above the horizon, their edges shifting like breath on a winter morning. The aurora is not merely a spectacle. It is the visible proof of an invisible truth, that Earth is guarded, even in silence. These lights are the gentle aftermath of a battle fought high above, where the magnetic field bends the sun's charged particles into graceful arcs instead of letting them tear into the atmosphere. Standing beneath such a sky, you can feel a stillness that seems older than anything human. The light moves slowly, without haste, as though it has all the time in the world. There is no sound here, no flash of violence, only the knowledge that what you see is the transformed remnant of something once dangerous. The magnetosphere, stretched thin and taut by the solar wind, is doing its work as it has for billions of years, and the Earth is breathing easily because of it. To early peoples, these lights were mysteries woven into the heavens. They told stories of spirits, of ancestors, of gods whose movements painted the night. Today, we can explain the process in terms of physics and chemistry, but the wonder remains untouched. Knowing that the aurora is the signature of our shield only deepens the sense of connection, for it reminds us that this beauty exists because our planet's heart still turns in the darkness. Under the aurora's glow, it is possible to imagine the scale of the forces at play. Above the colors is the magnetosphere, a vast and invisible structure stretching tens of thousands of kilometers into space. Beneath your feet, the outer core is churning in slow, powerful currents, generating the field that makes this scene possible. Between these two realms, the deep interior and the edge of space, lies everything we know, every breath, every drop of water, every leaf stirred by the wind. There is a kind of humility in standing here. The shield asks nothing of us. It does not demand maintenance, tribute, or gratitude. It simply works because the Earth's own heat and motion sustain it. And yet, without it, the world would be unrecognizable. Air thinned to a whisper, oceans faded to memory, the surface scoured by radiation. The lights above are not only beautiful, they are reassuring, a quiet affirmation that the deep machinery of the planet is still alive. One day, the auroras will shine for the last time. The core will cool, the dynamo will falter, and the shield will fade. But that day lies far beyond our horizon. For now, and for countless generations yet to come, we live under the silent light, beneficiaries of a protection so complete we rarely notice it. The sky glows not just for beauty's sake, but as a gentle reminder. We are sheltered, and that shelter is the reason we are here to see it at all. Imagine waking on a planet where the air is thin and harsh, where the sun's glare cuts unfiltered through the sky, and where every breath tastes of dust. The seas, if they exist at all, are shallow and shrinking, their surfaces shivering under the constant pressure of the solar wind. Without the shield, this could have been Earth's story, a world eroded not by time alone, but by the relentless hand of its star. Without the magnetic field, the solar wind would pour directly into the upper atmosphere, striking molecules with enough force to knock them free of the planet's grip. Hydrogen, light and quick, would be the first to go, slipping into space and carrying with it the potential for water. Oxygen would follow in slower measure, oxidizing the surface until rocks turned rust red, as they did on Mars. Over centuries, the pressure of the atmosphere would fall, the climate would swing wildly, and the surface would be bathed in levels of radiation that no unprotected life could endure. The loss would not be immediate, but it would be inevitable. Oceans would evaporate under the combined heat of the sun and the thinning of the atmosphere's protective blanket. Clouds would vanish, unable to form without enough water vapor, leaving the land exposed to the full force of day and the bitter cold of night. Winds would scour the ground, carrying fine dust into the air, where it would hang in a reddish haze. Life, if it had ever begun, would be forced into hiding, perhaps clinging to underground aquifers or retreating to the deep ocean floor, where layers of rock and water could still block the radiation. The diversity and abundance we know today would never have had the chance to appear. Without the shield, evolution's canvas would have been painfully small, limited to what could survive in perpetual shadow. This is not just an exercise in imagination. Mars shows us the outlines of such a fate. Riverbeds that no longer flow, ice caps that release vapor only to see it vanish into space. a sky so thin that even a light breeze feels foreign. And Venus, though it still holds a thick atmosphere, lacks a magnetic shield and is battered by charged particles in ways that strip elements from its upper layers, adding to its already inhospitable nature. Earth's survival is not a given. It is the result of a rare combination of conditions, chief among them a molten core that has kept the magnetic field alive for billions of years. Without it, we would not walk under blue skies or sail across wide oceans. We would not look up at the aurora and see beauty. Instead, the skies would tell a story of loss. The shield does not simply protect us. It allows Earth to be Earth. Deep in the planet's center, far beyond the crust we walk upon and the mantle that shifts slowly over ages, lies the heart of the Earth's magnetic power. The inner core. It is a sphere of solid iron and nickel, dense beyond imagination, pressed into solidity by pressures so great that even temperatures hotter than the surface of the sun cannot melt it. But it was not always there. The inner core is a relatively recent arrival in Earth's history, a child of the planet's slow cooling. Billions of years ago, the core was entirely molten, a vast ocean of liquid metal churning in complete darkness. As the Earth radiated its heat into space, the temperature within the very center dropped until iron began to crystallize. From that moment on, the inner core began to grow. Each year, an almost imperceptible layer of solid metal formed around its surface, locking in place while releasing heat and lighter elements into the outer core. This slow growth became one of the great engines of the geodynamo. The release of heat drives convection, stirring the molten outer core into powerful, spiraling currents. The lighter elements, pushed outward as iron solidifies, create buoyancy that further fuels the motion. Together, these processes sustain the movement needed to keep the magnetic field strong. In a way, the birth of the inner core was like the tightening of a bowstring. It gave the dynamo a new, enduring source of energy. The inner core also holds clues to Earth's deep history. Seismic waves from earthquakes, passing through it, reveal patterns of alignment in its crystal structure. These patterns hint that the core may rotate at a slightly different speed than the rest of the planet, and that its growth is not perfectly symmetrical. Some parts may be older than others, whispering of ancient shifts in the flow of the molten metal around it. Without the inner core, the outer core's motion would still be driven by leftover heat from Earth's formation and the decay of radioactive elements, but over time those sources would wane. The dynamo would weaken, the magnetic field would thin, and the shield would falter. The formation of the inner core extended the life of the magnetic field, perhaps by billions of years, long enough for complex life to emerge, evolve, and thrive. It is strange to think that something so vital to our survival grows in silence, hidden from us by thousands of kilometers of rock and metal. We cannot see it, cannot touch it, and yet it shapes our daily lives in ways we rarely consider. Every compass needle pointing north, every aurora dancing over the poles, every molecule of air and drop of water held close to the planet owes its safety to the work begun when the first crystal of iron formed at the center of the world. Surrounding the solid sphere of the inner core lies an ocean unlike any other, a realm of molten iron and nickel, swirling and boiling in perpetual darkness. This is the outer core, a place where temperatures soar above 4,000 degrees Celsius, yet the pressure is not quite enough to force the metal into solidity. Here, the motion never stops. Vast currents rise and sink, twisting into spirals under the influence of Earth's rotation. This is the restless heart of the geodynamo, the true generator of the magnetic field. The movement is driven by two main forces. First, heat flows outward from the inner core, rising through the molten metal and setting it into convection. Second, the crystallization of the inner core releases lighter elements, perhaps sulfur, silicon, or oxygen, into the outer core, making them buoyant. These buoyant regions rise while cooler, heavier metal sinks, creating a constant turnover. The planet's rotation then shapes this motion into columns and spirals that align with its axis, organizing the chaos into patterns capable of producing a stable magnetic field. The scale of this motion is almost impossible to imagine. The outer core is more than 2,000 kilometers thick, and its currents move with a power that dwarfs any storm on the surface. Yet they flow at speeds of only a few tens of kilometers per year. A slow, inexorable stirring that, over time, carries enough energy to maintain a shield reaching tens of thousands of kilometers into space. But the outer core is not entirely predictable. Like the atmosphere above us, it experiences turbulence and irregular shifts. These changes ripple upward, altering the shape and strength of the magnetic field at the surface. Over years and centuries, they cause the magnetic poles to drift, sometimes slowly, sometimes with surprising speed. At other times, they weaken parts of the field, allowing small windows where the shield is thinner than usual. Scientists study these motions indirectly, using variations in the magnetic field and seismic waves from earthquakes as clues. They have found hints of large eddies, of regions where the flow is faster or slower, and of patterns that may foreshadow reversals of the field. The restless outer core is a place of constant renewal, but also of constant change, reminding us that the magnetic shield is alive because the world beneath our feet is never still. In the end, the outer core's restlessness is a gift. Without its endless motion, the field would fade, the shield would vanish, and Earth would slowly lose the air and water that sustain life. Every turn of molten metal beneath us is a quiet act of preservation, a stirring of the planet's deep engine to keep the world above thriving. The shield we depend on is not fixed in stone. It is forged anew every moment in the restless depths below. Far above the clouds, beyond the thin veil of our atmosphere, lies a region where the magnetic field does more than deflect the solar wind. It traps it. Here, charged particles from the sun and from distant cosmic sources are caught in Earth's magnetic embrace, spiraling endlessly along its invisible lines of force. These regions are called the Van Allen radiation belts, and they are like vast, invisible moats surrounding our world, standing watch over the planet below. There are two main belts. The inner belt, closest to Earth, is dominated by high-energy protons, many born from cosmic rays colliding with atoms in the upper atmosphere. The outer belt, farther away, is filled mostly with electrons, their numbers swelling and shrinking in response to the sun's changing moods. Between them lies a quieter zone, though even this space is not entirely empty. Particles drift through like whispers between walls. To the human eye, the belts are unseen. But to spacecraft, they are a region of danger. The trapped particles move at near-light speeds, and their energy can damage electronics, disrupt communications, and pose risks to astronauts passing through. This is why missions to the Moon or other planets plot their courses carefully, skimming through the belts as quickly as possible. Yet for all their hazards to our machines, the Van Allen belts are an integral part of the planet's defenses. They act as reservoirs, catching and holding particles that might otherwise strike the atmosphere directly. Some of these particles eventually leak downward along magnetic field lines, fueling auroras at high latitudes. Others are slowly drained away into space, their paths bent and altered until they no longer threaten the planet. In this way, the belts are both guardians and gatekeepers, managing the energy that flows between the Earth and the space beyond. The belts are not static. Solar storms can flood them with new particles, swelling their boundaries and intensifying their energy. At other times, waves within the belts can scatter particles outward, thinning their numbers. This constant flux is another expression of the magnetic field's dynamism, a reminder that even far from the surface, the shield is a living system, shaped by both the deep core and the distant sun. In a sense, the Van Allen belts are a visible signature of the invisible shield. If you could see them, they would appear as great, donut-shaped rings encircling the Earth, glowing faintly with the energy of countless trapped particles. They are silent sentinels, never sleeping, always turning, proof that our planet's defense extends far beyond what we can touch or see. And like all parts of the magnetic field, they exist only because the molten heart of the Earth continues to beat far below. The sun is not the steady, gentle star it appears to be when we look up from Earth's surface. Beneath its calm, golden glow lies a restless engine of nuclear fire, constantly roiling with motion. Its surface, seething with boiling plasma, twists and tangles magnetic fields until they snap, unleashing bursts of energy powerful enough to affect worlds millions of kilometers away. These events, known as solar storms, are among the most dramatic expressions of our star's nature. A solar storm begins quietly, deep within the sun's convective layers. Magnetic fields, stretched and twisted by the sun's rotation, become knotted and unstable. When they break, they release their stored energy in colossal flares, emitting radiation across the spectrum, from radio waves to X-rays, and sending waves of charged particles into space. Sometimes these events are accompanied by coronal mass ejections, immense clouds of solar plasma hurled outward at speeds of millions of kilometers per hour. When such a storm is aimed toward Earth, it becomes a test of the planet's magnetic shield. The solar wind thickens and quickens, pressing against the magnetosphere and compressing it on the day side while stretching it into a long tail on the night side. Shock waves race through the field, and lines of magnetic force can snap and reconnect, hurling particles toward the poles with sudden violence. From the ground, the most visible result is the aurora, often brighter, more widespread, and more turbulent than usual. Curtains of green and violet may sweep across skies far from the poles, a reminder that something powerful is unfolding above. But not all the effects are beautiful. Solar storms can disturb the currents in Earth's upper atmosphere, interfering with satellite operations, disrupting radio communications, and even causing surges in electrical grids. Without the magnetic field, the consequences would be far more severe. The full brunt of the storm's particles would slam into the atmosphere, stripping away gases and heating the upper layers to the point where escape into space becomes easier. Over time, repeated storms could erode the atmosphere itself, as they likely did on Mars after its magnetic field faded. The shield does not block every particle. Some slip through, guided along field lines toward the poles, but it absorbs and redirects enough to keep the planet safe. Each storm becomes part of the ongoing conversation between the Sun and Earth, a surge of energy met with a graceful deflection. In this sense, solar storms are not simply threats. They are also reminders of the shield's purpose and power. Long after the flare has faded from the Sun's surface and the ejected cloud has passed beyond Earth, the magnetosphere settles back into its usual shape. The lights fade from the sky, and calm returns. Yet deep within the outer core, the molten metal continues its slow, steady churn, ensuring that when the next storm comes, and it will, the shield will rise to meet it. On the night side of Earth, opposite the Sun, the magnetic field stretches far into space, drawn out into a vast, tapering structure known as the magnetotail. It is the hidden half of the shield, the part that never sees the daylight but plays a crucial role in the planet's defense. If the day side of the magnetosphere is like a sturdy shield raised against the solar wind, the night side is like a cloak that trails behind, absorbing and redirecting the energy that slips past the front lines. The magnetotail forms because the solar wind presses constantly on the side of the field facing the Sun, squeezing it inward. On the opposite side, the magnetic field is pulled outward, stretching into a long cylinder that can extend hundreds of thousands of kilometers into space, more than the distance to the Moon. Within this tail, lines of magnetic force run parallel to the flow of the solar wind, enclosing vast regions of trapped plasma. But the magnetotail is not a static structure. It is a place of tension and release. Sometimes, the stretched field lines snap and reconnect in an event called magnetic reconnection, releasing stored energy back toward Earth. This energy travels down the magnetic field lines toward the polar regions, where it ignites bright auroras and accelerates particles into the atmosphere. These reconnection events are like deep, invisible tides, sudden surges that carry the Sun's influence all the way into the night sky. For spacecraft traveling in the magnetotail, the environment is both strange and dynamic. Instruments detect flows of charged particles rushing in opposite directions, sudden bursts of energy, and shifting boundaries between regions of different plasma density. To scientists, this data tells the story of how Earth's magnetic field interacts with the solar wind not just by resisting it, but by reshaping and channeling it far downstream. The magnetotail also has a role in protecting the planet. Some of the particles captured within it eventually escape into space along the tail's length, carried away from Earth instead of toward it. Others are funneled back toward the atmosphere in ways that are less damaging than a direct solar wind impact. In this way, The tail serves as both a buffer and a release valve, managing the energy and matter that the sun sends our way. Though we cannot see it from the ground, the magnetotail is as much a part of the shield as the auroras that dance over the poles. It is the quiet guardian of the dark side of Earth, standing watch in a place where night never ends. And like every part of the magnetosphere, it exists only because the molten heart of the planet continues its endless, unseen motion far below our feet. Life on Earth has never existed without the magnetic field. From the very first microbes that stirred in the oceans to the complex web of species that now fills the planet, every living thing has been shaped, in some way, by the quiet presence of the shield. It is not simply a protector from above. It has influenced where life could survive, how it could evolve, and the stability of the environments that cradle it. In the early days, before the atmosphere was rich in oxygen, the magnetic field was one of the only defenses against the sun's harsh radiation. It allowed fragile molecules to persist in shallow waters and on sunlit shores without being broken apart too quickly. Without that protection, the chemistry of life might have been forced into permanent hiding, deep underground or far below the ocean's surface, where sunlight could never reach. The shield gave life access to light while keeping the worst of its dangers at bay. A balance that fueled photosynthesis, oxygen production, and the eventual transformation of the atmosphere. As life grew more complex, the shield continued to shape its possibilities. Stable climates depend in part on the retention of air and water, and those are only possible when the atmosphere is not stripped away by the solar wind. With the shield in place, Earth maintained the air that moderates temperature, cycles water, and provides the gases life needs. Over millions of years, this stability allowed ecosystems to establish roots. Forests, coral reefs, grasslands, all of them depending on the same protective bubble. Even migration patterns in the animal kingdom bear the shield's imprint. Many creatures, from sea turtles to birds, can sense Earth's magnetic field, using it as a guide in their long journeys across oceans and continents. This magnetic sense, honed over countless generations, is possible only because the field is strong and consistent enough to be a reliable map. Humans, too, have benefited in ways both direct and indirect. Our civilizations arose under skies free from the relentless stripping of atmosphere, in climates made possible by the shield's defense of air and water. We learned to navigate the seas with compasses that relied on its pull. We built cities without the constant threat of dangerous radiation pouring through the sky. We have grown so accustomed to this safety that it is easy to forget it exists at all. Without the magnetic field, the story of life here would almost certainly have been shorter, smaller, and hidden. With it, Earth has become a place where life not only survives but flourishes in the open, stretching from the deepest trenches to the highest mountains, from icy poles to sunlit deserts. The shield has always been more than just a defense. It has been the stage upon which life's entire drama unfolds. The magnetic field may be invisible, but it leaves a record that can outlast mountains. Locked within ancient rocks, frozen into minerals, is a history of the shield that stretches back billions of years. These stones are silent witnesses, preserving the directions and strengths of magnetic fields long vanished, telling us not only that the shield has endured, but how it has changed over time. The key to this memory lies in certain minerals, especially those rich in iron like magnetite. When molten lava cools, or when sediments settle and harden, these minerals align themselves with the magnetic field, like tiny compasses fixed in place. Once locked in position, they carry the imprint of the field's direction and intensity at the moment of their formation. This natural archive is called paleomagnetism, and it allows scientists to reconstruct the history of Earth's magnetism across eons. By studying these magnetic signatures, researchers have discovered that the field has flipped polarity many times, with the north and south magnetic poles trading places. They have also traced how the poles wander between reversals, drifting unpredictably over decades and centuries. Some rocks even record periods when the field weakened dramatically, hinting at moments when the shield's strength wavered before recovering. The oldest magnetic signals come from ancient crystals called zircons, found in the rocks of Western Australia. These tiny, resilient minerals have survived for more than 4 billion years, and some contain evidence suggesting that a magnetic field existed surprisingly early in Earth's history. If true, it means that the shield began its work not long after the planet formed, early enough to protect the young atmosphere and help preserve the water that would later host life. On the ocean floor, new volcanic rock is constantly forming at mid-ocean ridges. As it cools, it records the field's direction, creating a pattern of magnetic stripes that mirror each other on either side of the ridge. These stripes are a map of reversals stretching back millions of years, laid out in perfect symmetry by the slow movement of tectonic plates. It was this pattern that helped confirm the theory of plate tectonics, showing that the continents and seafloors move while the field above them flips and changes. Each rock, each mineral, is a page in a story far longer than human memory. Together, they tell us that the shield has been a constant presence, adapting and renewing itself through changes that would seem immense on any human timescale. They remind us that the magnetic field is not static but alive, shaped by forces deep within the planet. And though we cannot see those forces directly, the stones speak for them, whispering of a guardian that has stood watch since the dawn of the world. The north and south magnetic poles are not fixed points etched into the planet's surface. They drift, sometimes slowly, sometimes with surprising speed, tracing paths across ice, ocean, and land. This wandering is a natural consequence of the restless flows in Earth's outer core, where the magnetic field is born. As the molten iron shifts, the structure of the field above it changes, and the poles follow like shadows cast by moving currents far below. The movement is not uniform. At times, the poles meander gently, covering only a few kilometers each year. At other times, they surge forward, traveling tens of kilometers annually. In the past century, for example, the North Magnetic Pole has accelerated in its journey from the Canadian Arctic toward Siberia, shifting more rapidly than at any time in recorded history. The South Magnetic Pole wanders as well, though its path is less closely tracked, given the remoteness of Antarctica. For most of human history, these shifts were little more than a curiosity, affecting only those who navigated by compass. But in our modern world, where navigation systems and communication technologies depend on precise models of the magnetic field, the pole's motion has practical consequences. Maps used for navigation must be updated regularly, and the World Magnetic Model, a mathematical representation of the field, must be recalculated every few years to keep pace with the wandering poles. To wildlife, however, the drifting poles are simply part of the environment. Many migratory species, from sea turtles to birds, navigate in part by sensing Earth's magnetic field. As the poles move, these animals adjust, guided not by fixed maps but by instincts shaped over millions of years of living under a field that is never truly still. The wandering poles also offer scientists valuable clues about the core's hidden dynamics. Sudden changes in direction or speed can signal shifts in the flow of molten metal deep below, or even hint at the early stages of a magnetic reversal. By tracking the poles with satellites and ground-based observatories, researchers can watch the magnetic field's surface expression and infer the invisible motions driving it from within. There is something humbling about this slow, patient migration. It reminds us that the map of our world is not only shaped by mountains, rivers, and coastlines, but also by forces we cannot see. The poles may wander for centuries without settling, and one day, they may trade places entirely. Yet through it all, the shield will remain, adapting to the currents of its own creation, protecting the planet as it has since the earliest days. At first glance, Earth's magnetic field and its climate seem to belong to entirely different realms. One a product of molten metal deep within the planet, the other shaped by sunlight, oceans, and air. Yet the two are quietly connected, bound together by the role the shield plays in preserving the atmosphere that makes climate possible. Without this invisible barrier, the patterns of wind, rain, and temperature we know would unravel, and the planet's climate would tilt toward extremes inhospitable to life. The shield's most direct influence on climate comes through its defense of the atmosphere from the solar wind. Without it, the sun's constant stream of charged particles would gradually erode the upper layers of air, carrying away light gases like hydrogen and, over time, oxygen and nitrogen as well. With less air, the atmosphere's ability to trap heat and distribute it across the planet would be weakened. Days would scorch under the unfiltered sun, and nights would plunge toward bitter cold, a world of violent contrasts. Water, too, would be at risk. The hydrogen from water molecules is especially vulnerable to escape when bombarded by solar wind particles. Without a shield, oceans would shrink over millions of years, feeding less moisture into the air, reducing cloud cover, and breaking the cycles that drive rainfall. Deserts would spread, rivers would dwindle, and the gentle moderation of temperature by water's presence would be lost. There is also a subtler link. The magnetic field helps preserve the ozone layer by limiting the amount of high-energy solar radiation that reaches the upper atmosphere. The ozone layer, in turn, blocks most harmful ultraviolet light from reaching the surface. Without it, not only would life be exposed to greater radiation, but chemical reactions in the atmosphere would shift, altering temperature balances and the movement of air. Evidence from other worlds supports this connection. Mars, with no active magnetic field, lost much of its atmosphere to the solar wind and now endures thin, dry air and dramatic temperature swings. Venus, without a global magnetic field but still holding on to a thick atmosphere, suffers from a runaway greenhouse effect, proof that losing the shield is not the only path to climate instability, but that its presence can help keep a planet's systems in balance. Earth's climate has certainly changed over time. Ice ages have come and gone, warm periods have followed cold, but the underlying stability of our atmosphere has remained. That stability owes much to the shield's endurance, ensuring that the raw material for climate, air, and water remains in place. As long as the core continues to turn and the shield holds, the climate will remain a canvas on which life can adapt, migrate, and flourish, rather than a battlefield against an unyielding sky. The sun we know today is steady by human standards, its light arriving each morning with a reassuring regularity. But in its youth it was a far more turbulent star. It spun faster, flared more often, and sent streams of charged particles into space with an intensity our modern world has never experienced. The young sun's wind was fierce and constant, capable of stripping away atmospheres and sterilizing the surfaces of unprotected worlds. This was the environment in which Earth's magnetic field was truly tested. The solar wind then was several times stronger than it is today, filled with bursts of plasma from frequent solar flares and coronal mass ejections. Each blast carried the potential to erode the upper atmosphere, heating it and driving its lightest molecules into space. Planets without strong magnetic fields, like Mars, were battered relentlessly, their skies thinning until little remained. For Earth, the difference was the shield. The geodynamo in the outer core had already awakened, stretching magnetic lines of force far into space. When the young sun storms came roaring through the solar system, they met this barrier first. The day side of the magnetosphere compressed under the pressure, but the night side stretched into an even longer tail, absorbing the sun's assault and redirecting much of its energy into harmless currents of light at the poles. The result was not just survival but preservation. The magnetic field allowed Earth to hold onto its early atmosphere, rich in carbon dioxide, nitrogen, and water vapor, and to maintain surface temperatures warm enough for liquid water. This stability, rare in the young solar system, gave the planet's oceans the time they needed to settle and remain, creating the stage on which life could eventually emerge. The young sun also bathed the planet in high levels of ultraviolet light, which could have been devastating to fragile, early molecules. But with the shield deflecting charged particles and helping preserve a denser atmosphere, that radiation was filtered and softened before it reached the surface. The protective interplay between field and atmosphere was already shaping Earth's destiny, even before the first living cells stirred in the water. In those ancient centuries, the magnetosphere was not a quiet, steady dome as we imagine it today. It was a living, shifting fortress, pushed and pulled by the sun's constant fury. Auroras may have been brighter and more frequent, not the occasional wonders of modern skies but regular spectacles, painting the poles in colors each time the sun's breath struck the field. And beneath that restless sky, Earth's surface remained a sanctuary in the making. It is difficult to overstate how much the shield mattered in those early days. Without it, the sun's youth might have stripped Earth bare long before life could take hold. Instead, The molten heart within the planet met the fiery heart of the sun and found balance. A fragile but enduring harmony that has lasted billions of years. As the ages passed, the sun began to slow its spin and settle into a calmer rhythm. Its flares became less frequent, its solar wind less fierce. The changes were gradual, stretching over hundreds of millions of years, but their impact on Earth was profound. The shield, still powered by the molten dynamo deep within the planet, found itself facing a gentler opponent. The constant strain of the young sun's tempests gave way to long stretches of relative calm, and the magnetosphere could expand, breathing outward into space. In these quieter years, the magnetic field's work shifted from emergency defense to steady preservation. The atmosphere, no longer battered as relentlessly, grew more stable. Water vapor lingered longer in the sky, clouds formed more predictably, and rainfall patterns began to settle. Oceans deepened, fed by rivers that carved valleys into the land. It was during these periods of stability that Earth's climate could refine itself, creating conditions where early life could flourish and diversify. The reduced pressure from the sun also allowed the magnetic field to maintain a broader shield. On the day side, the magnetosphere stretched farther from the surface, intercepting solar wind before it could even graze the upper atmosphere. On the night side, the long tail of the field remained a dynamic reservoir, occasionally releasing bursts of energy during magnetic reconnection events, but without the constant violent strain of the past. For life, these changes were transformative. Early microbes, once confined largely to sheltered environments, beneath water, under ice, or hidden in the shadows, could begin to venture into more open spaces. Sunlight, filtered by an increasingly complex atmosphere, became less a threat and more a source of energy for photosynthesis. With the shield holding steady, life could spread, adapt, and evolve without the constant backdrop of a storm-lashed world. Yet the quiet did not mean inactivity. The sun still sent flares and occasional storms, and the shield continued its dance, flexing and reshaping to meet each one. But these events were now interruptions in a larger pattern of calm, rather than the defining character of the sun's relationship with Earth. The balance between star and planet had shifted, and for the first time in its history, Earth could experience long, uninterrupted epochs of relative peace. It was in this quieter sunlight that life's first great transformations began. The slow oxygenation of the atmosphere, the development of more complex cells, and the groundwork for the biodiversity that would one day fill every corner of the globe. And through it all, the shield remained as it had from the beginning. Silent, invisible, essential. About 2.4 billion years ago, Earth underwent one of the most profound transformations in its history. Known as the Great Oxidation Event, it marked the first time oxygen became a significant and permanent part of the atmosphere. Before this, oxygen existed only in fleeting traces, produced by primitive photosynthetic organisms but quickly consumed by chemical reactions with the planet's surface and oceans. Then, slowly, it began to accumulate, and once it crossed a certain threshold, the planet's chemistry, climate, and future were forever changed. The rise of oxygen was made possible in part by the magnetic shield. Without it, the early atmosphere might have been stripped away before photosynthetic life could gain a foothold. The shield not only protected the gases that were already there but also preserved the conditions necessary for cyanobacteria, those tiny architects of the oxygen revolution, to thrive in sunlit waters. Shielded from the worst of the solar wind's charged particles, these organisms could spread and multiply, transforming sunlight into chemical energy and releasing oxygen as a byproduct. As oxygen levels climbed, it began to react with dissolved iron in the oceans, forming vast deposits of iron oxide, banded iron formations that still stripe ancient rocks today. This process slowly cleared the seas of excess iron, allowing oxygen to remain dissolved in the water and, eventually, to spill over into the air. The magnetic field, by defending both air and water from erosion, ensured that this slow buildup was not undone by the sun's relentless wind. The consequences of the Great Oxidation were double-edged. For many existing microorganisms, oxygen was toxic, triggering one of the earliest mass extinctions in Earth's history. But for others, it opened entirely new possibilities. Oxygen-rich environments allowed for more efficient energy production, paving the way for more complex cells and, much later, multicellular life. This transformation reshaped ecosystems and altered the course of evolution permanently. The shield's role in this was indirect but critical. By holding onto the atmosphere over immense spans of time, it gave biology the stability it needed to experiment, adapt, and eventually reinvent itself. Without that protection, oxygen might never have accumulated in such abundance, and the energy-rich environments necessary for complex life might never have formed. Looking back, it is clear that the Great Oxidation was not just a story of microbes and chemistry, it was also a story of deep planetary partnership. The molten heart beneath our feet, the field it generated, and the fragile cells floating in ancient seas were all part of the same unfolding narrative. The shield did not create life, but it gave life the stage and the time it needed to transform the world. In the deep past, long before humans could record them, magnetic storms swept across Earth with a power we can scarcely imagine today. The young sun, still more active than it is now, hurled bursts of plasma and streams of high-energy particles into space on a regular basis. When these surges struck the planet, the magnetic field shuddered and flexed, bending under the pressure before springing back with renewed force. During such storms, the day side of the magnetosphere would compress dramatically, pushed inward toward Earth by the sheer momentum of the solar wind. On the night side, the magnetotail stretched even farther into space, storing vast amounts of energy in its taut magnetic lines. Then, in sudden bursts, these lines would snap and reconnect, sending charged particles racing back toward the planet's poles. The skies during these events would have been breathtaking. Auroras would bloom not only near the poles but far closer to the equator, painting tropical nights with rippling veils of green, red, and violet. These displays might have lasted for days, growing brighter and more turbulent as waves of particles cascaded into the upper atmosphere. Even in the ancient oceans, the light could have shimmered faintly through the water's surface, a fleeting glow in an otherwise dark and silent world. But the beauty of these storms masked their raw power. High-energy particles colliding with the atmosphere could alter its chemistry, producing short-lived compounds like nitrogen oxides that might have affected climate patterns in subtle ways. In the absence of the magnetic field, such storms could have stripped away significant amounts of atmosphere, accelerating the loss of water and thinning the protective layers of air. The shield's ability to absorb, redirect, and transform that energy was the difference between a temporary disturbance and a lasting wound. For early life, these storms may have been both challenge and opportunity. While bursts of radiation could damage delicate molecular structures, they also delivered energy capable of driving chemical reactions that built complexity. As long as the shield held, life could survive the challenge and, perhaps, even benefit from the energy that passed through in controlled measure. We cannot see those ancient storms now, but their echoes are preserved in the rocks and ice. Layers of certain isotopes, like beryllium-10, formed in the atmosphere during intense solar events can be found in ancient sediments, silent records of times when the sun's breath grew fierce. Together, these traces and the continued presence of the magnetic field tell a story of resilience. A planet tested again and again, yet never stripped bare. High above the surface, in a thin band of the stratosphere, lies one of Earth's most vital defenses, the ozone layer. This fragile blanket of gas absorbs most of the sun's harmful ultraviolet radiation, filtering the light that reaches the ground so that life can flourish without being scorched. While the ozone layer is a product of atmospheric chemistry, its long-term survival is closely linked to the work of the magnetic field. The shield's role begins with its constant deflection of the solar wind. Without that protection, charged particles from the sun would stream directly into the upper atmosphere, colliding with molecules and breaking them apart. These collisions could disrupt the delicate balance of reactions that create and maintain ozone. In particular, intense bombardment could produce large amounts of nitrogen oxides and hydrogen oxides, compounds that destroy ozone molecules faster than they can be replaced. We have glimpses of what such damage might look like. Even today, strong solar storms can temporarily deplete ozone at high latitudes, where energetic particles penetrate deeper into the atmosphere. These events are usually short-lived, But in a world without a magnetic field, the impact would be relentless, eroding the ozone layer until it could no longer shield the surface from ultraviolet light. The consequences would reach far beyond discomfort or sunburn. Excessive UV radiation damages the DNA of living organisms, disrupting reproduction and increasing mutation rates. In plants, it can impair photosynthesis, stunting growth and disrupting entire ecosystems. In the oceans, it can harm the phytoplankton that form the base of the marine food web, reducing the oxygen they produce and the carbon they absorb. By preserving the ozone layer's stability, the magnetic field plays an indirect but essential role in sustaining life's complexity. It ensures that the chemical reactions in the atmosphere can proceed under relatively steady conditions, allowing the ozone layer to recover from natural fluctuations and resist long-term collapse. This quiet partnership between shield and sky has existed for billions of years, shaping the habitability of Earth in ways we are only beginning to appreciate. It is easy to think of the shield as guarding us only from what lies beyond, charged particles, cosmic rays, solar wind. But its influence reaches inward as well, touching the chemistry of the air we breathe and the light that warms our skin. The magnetic field and the ozone layer are two different kinds of protection, born of different processes, yet they are entwined. One deflects danger at the gates, the other filters what comes through, and together they have allowed life to spread from the depths of the ocean to the peaks of the mountains. Earth's history is marked by moments when life faltered, mass extinctions that reshaped the planet's ecosystems and reset the course of evolution. Many of these catastrophes were driven by forces such as volcanic upheavals, asteroid impacts, and abrupt climate shifts. Yet in the background, the magnetic shield was always present, influencing both the severity of these events and the recovery that followed. When the shield is strong, it buffers life from the added stress of heightened radiation. In times of environmental crisis, this protection can mean the difference between species clinging to survival and vanishing entirely. For example, after a major asteroid impact, debris lofted into the atmosphere can weaken the ozone layer, allowing more ultraviolet light to reach the surface. If, on top of that, the magnetic field were weak or unstable, the increase in harmful radiation would be even greater, slowing the recovery of surviving life. There is evidence that during certain extinction events, the shield's strength may have been reduced. In some geological layers, scientists have found signs of increased cosmogenic isotopes, atoms created when cosmic rays strike the atmosphere, suggesting that more radiation was penetrating from space. These periods of weaker shielding might have coincided with reversals or excursions of the magnetic field, compounding the effects of other environmental stresses. Even in the absence of mass extinction, fluctuations in the shield's power can subtly shape ecosystems. A slightly weaker field allows more cosmic radiation to influence atmospheric chemistry, which in turn can alter climate patterns or the distribution of ozone. Over thousands of years, these changes can ripple through food webs, shifting the balance of species and habitats. Yet perhaps the shield's most important role in Earth's long story of extinction and recovery is its constancy. Through every upheaval, whether it was the end of the dinosaurs or the devastation of the Permian extinction, the field has always returned to full strength. This resilience has given life a stable platform from which to rebuild, ensuring that even after the most devastating losses, the conditions for complexity and diversity would return. It is a reminder that the survival of life is never determined by a single factor. The shield does not prevent every catastrophe, but it shapes the boundaries of what is survivable. Without it, the history of life on Earth might have been a series of false starts, bursts of evolution followed by complete collapse. Instead, the magnetic field has been a silent partner through every trial, steadying the planet's course through deep time. Every time the aurora shimmers above the poles, it is telling a story older than humanity, older even than life on land. These curtains of light are more than a fleeting spectacle. They are the living memory of a process that has protected the Earth for billions of years. Long before human eyes looked up in wonder, auroras danced over icy seas and barren continents, marking the moments when the magnetic field met the energy of the sun and transformed it into beauty. In the earliest epochs, the young sun storms were fierce and frequent. The auroras then would have been brighter, wilder, and far more common than they are now. They would have flared not just at the poles, but across vast swaths of sky, sometimes reaching the equator during the most violent events. These luminous displays were the visible signature of the shield's constant work, each glow a sign that particles from the solar wind had been captured and tamed. Their destructive force dissipated harmlessly into the upper atmosphere. For early life, simple, microscopic, and mostly hidden in the oceans, these lights had no meaning. Yet they were a part of the same protection that allowed such life to exist. The auroras were the shield speaking in color, showing that the invisible lines of force around the planet were holding strong against the sun's assaults. Even now, when the lights ripple across the night, they are a reminder of that same enduring defense. When humans finally appeared and began to wander under the polar skies, the aurora became woven into our myths and cultures. To some, they were the spirits of ancestors. To others, they were omens, blessings, or warnings from the gods. These stories, passed down through generations, were an intuitive recognition of something we now understand scientifically: that these lights connect us directly to the sun, to space, and to the deep heart of the earth. The colors we see: green from oxygen at lower altitudes, red from oxygen higher up, blues and purples from nitrogen, are not just beautiful. They are fingerprints of the atoms and molecules that make up our atmosphere, glowing in response to the energy delivered along magnetic field lines. Each ripple, each arc of light, is the end of a journey that began millions of kilometers away on the surface of the sun. In this way, the aurora is both present and ancient. It is happening in real time, yet it is also a continuation of a dance that began when the geodynamo first awakened in Earth's core. It is our most visible link to the shield, a living thread that ties us to the deep past and, if the shield endures, will connect us to the distant future. Whenever we look up at those moving colors, we are looking at an ancient memory made light, proof that the Earth remembers how to protect itself, and us. When humanity first reached beyond the atmosphere, we discovered just how far the shield's influence extends. Astronauts orbiting Earth, satellites drifting through space, and probes sent to other planets have all revealed the invisible architecture of the magnetosphere. Instruments confirmed what science had long suspected. The magnetic field is not a vague bubble, but a vast and dynamic structure, stretching tens of thousands of kilometers into space on the sun-facing side and forming an immense tail that reaches far beyond the moon's orbit. In the space age, the shield's value is measured not only in the protection it gives to life on the surface, but also in the safety it provides for our technology and explorers. Satellites in low Earth orbit remain well within the magnetosphere, shielded from much of the radiation that would otherwise damage electronics and shorten their lifespans. Astronauts aboard the International Space Station benefit from the same protection, venturing only briefly into regions of higher radiation when passing through the edges of the Van Allen belts. Yet the space age has also shown us the shield's limits. During strong solar storms, bursts of charged particles can penetrate deeper into the magnetosphere, creating hazards for satellites, disrupting communications, and, in rare cases, causing power grid failures on the ground. These events have made it clear that the magnetic field is not an impenetrable wall, but a living, flexible barrier that must constantly adjust to the sun's moods. Spacecraft have flown through the magnetopause, the outer boundary where the solar wind meets the magnetic field, and into the magnetotail, sampling the charged particles and measuring the currents that flow along magnetic field lines. These missions have revealed that the shield is not static but constantly reshaped by the solar wind, its boundaries shifting in and out depending on the sun's activity. Beyond Earth, our probes have visited worlds without such protection, and the difference is stark. On Mars, instruments recorded a direct interaction between the solar wind and the atmosphere, stripping away gases into space. On the Moon, which lacks both a magnetic field and atmosphere, the surface bears the marks of countless unfiltered impacts from solar and cosmic particles. These comparisons have deepened our understanding of just how exceptional Earth's magnetic cocoon is, and how vital it has been to our history. In the space age, the shield has also become a navigational aid, not just for compasses on the ground but for spacecraft that use its structure to orient themselves. Its lines of force guide not only migrating birds but also streams of charged particles that power experiments and help us probe the mysteries of plasma physics. Looking outward from this vantage point, the magnetosphere appears as our planet's signature in space. a unique halo of protection that announces the presence of a living, active world. And as we journey farther from home, we carry with us a new appreciation for the shield, not as an abstract concept, but as the constant companion that has made exploration and life itself possible. For centuries, humans have used compasses to find their way, trusting a slender needle to point toward magnetic north. What began as a simple tool for navigation has, in the space age, evolved into a sophisticated science of mapping the magnetic field in exquisite detail. Today, fleets of satellites, ground observatories, and ocean-based sensors work together to trace the shield's every curve and shift, revealing a living structure that changes from day to day, year to year. Mapping the magnetic field begins with measuring its strength and direction at many points around the globe. Satellites such as the European Space Agency's swarm constellation fly in coordinated orbits, sampling the field from different heights and positions. On the surface, magnetometers at observatories track variations over minutes, hours, and decades. Even ships and aircraft contribute, gathering readings as they cross oceans and skies. Each measurement is a thread, and when woven together, they form a map of the shield's invisible weave. These maps reveal patterns that would otherwise remain hidden. They show the wandering paths of the poles, the regions where the field is stronger or weaker, and the subtle ripples caused by currents in the molten outer core. They also capture the field's response to solar storms, recording the sudden compressions and expansions of the magnetosphere as the solar wind changes. One of the most intriguing findings from mapping efforts is the South Atlantic anomaly, a vast region over South America and the South Atlantic Ocean where the magnetic field is unusually weak. Here, satellites passing overhead encounter higher levels of radiation, and spacecraft operators must take special precautions to protect sensitive electronics. The anomaly is thought to be linked to complex flows in the outer core, perhaps even signaling the early stages of a larger shift in the field. Mapping the invisible has become more than an academic pursuit. It is essential for modern life. The World Magnetic Model, built from these observations, underpins everything from smartphone navigation to military operations, from shipping routes to aviation safety. As the field changes, the model must be updated, ensuring that the tools we rely on continue to point us true. Yet beyond its practical uses, mapping the magnetic field carries a deeper significance. It allows us to see the heartbeat of the planet, to watch the shield as it flexes and breathes in response to the deep motions of the core and the distant moods of the sun. It is a reminder that even in a world saturated with visible landmarks, mountains, rivers, forests, there are landscapes of force and energy that can only be charted through patient observation and the merging of countless small measurements. To map the invisible is, in a way, to bring the unseen closer to us, to transform the magnetic field from an abstract concept into a tangible part of our home. And as long as we continue to watch it, we will be better prepared for whatever changes the shield may reveal in the years and centuries ahead. Far above the rolling waves of the South Atlantic Ocean, there is a place where Earth's protective shield grows thin. This region, stretching over South America and the adjacent ocean, is known as the South Atlantic Anomaly. To the human eye, there is nothing unusual here, no strange colors in the sky, no shimmering lights, but to satellites and astronauts passing overhead, it is a place of heightened risk, where the magnetic field's grip on charged particles is unusually weak. The anomaly exists because Earth's magnetic field is not perfectly aligned with its rotational axis, nor is it uniform in strength. Deep in the molten outer core, the churning currents of liquid iron create irregularities in the field, like eddies in a vast, unseen river. In the South Atlantic, one of these irregularities pushes the inner Van Allen radiation belt closer to the planet's surface than anywhere else. For satellites orbiting through this zone, the effect is immediate. Instruments are exposed to higher levels of energetic particles, which can disrupt electronics, cause data errors, or even damage sensitive components. Operators sometimes shut down certain systems temporarily when passing through the anomaly, treating it almost like a patch of rough weather in space. Astronauts aboard the International Space Station, when their orbit carries them over this region, report more frequent flashes of light in their vision, tiny bursts of radiation interacting directly with their retinas. Scientists watch the South Atlantic anomaly closely because it is not static. Over the past decades, it has been slowly drifting westward and expanding, its weakest point growing weaker still. Some researchers suspect it may be linked to deeper changes in the core, possibly even an early sign of a future magnetic reversal. Others view it as a normal fluctuation in the shield's complex, ever-shifting pattern. Whatever its cause, the anomaly serves as a reminder that Earth's magnetic field is not a fixed fortress, but a dynamic, living system. It can stretch, bend, weaken, and recover, often in ways that surprise us. It also underscores how deeply we now depend on the shield not just for life itself, but for the technology we've woven into our daily existence. In a world where satellites guide airplanes, ships, and even the phones in our pockets, a weakness in the field has consequences that ripple far beyond the upper atmosphere. For now, the South Atlantic anomaly is not a threat to life on the surface. Our atmosphere still blocks most harmful radiation, but it is a window into the restless heart of the planet. Deep below, in the liquid iron currents of the core, something is shifting, and the anomaly is its signature on the skin of the magnetic field. Watching it change is like watching the faint tremor of a sleeping giant, never quite sure what it will do next. At first glance, the magnetic poles might seem like fixed points, anchors at the top and bottom of our world. But in truth, they are restless travelers, forever drifting across the surface of the planet in slow, unpredictable paths. This motion, called polar wandering, is one of the clearest signs that the magnetic field is a living phenomenon, shaped by the restless flow of molten iron deep within Earth's core. The North Magnetic Pole, in particular, has been moving with surprising speed in recent decades. In the early 20th century, it ambled along the Canadian Arctic, shifting only a few kilometers each year. But by the turn of the 21st century, it began racing toward Siberia at nearly 55 kilometers per year, a pace that startled scientists and forced updates to navigation systems much sooner than expected. This wandering is not random. Beneath the crust, in the molten outer core, vast streams of liquid iron generate magnetic fields that combine, reinforce, or cancel each other out. When the balance between these flows changes, the location of the poles shifts accordingly. The South Magnetic Pole wanders too, though its path is less precisely tracked due to its remote position over Antarctica. For most of human history, such movements have had little effect on daily life. But in our era of precision navigation, where airplanes, ships, and even smartphones rely on the world magnetic model, pole positions must be updated regularly. The sudden acceleration of the North Pole's drift in recent years has meant revising the model ahead of schedule to ensure accuracy for everything from GPS devices to military operations. Some scientists see the pole's motion as part of the magnetic field's natural variability, while others wonder if it might be a precursor to a larger change, perhaps even a full reversal in which North and South trade places. Historical records from the geological record show that reversals have happened many times before, sometimes preceded by a period of rapid pole wandering. Still, for now, the poles remain strong, and their journey is more a curiosity than a crisis. Yet watching them roam across the globe is a humbling reminder. Even the points on which our compasses depend are not truly fixed. The shield is not a rigid shell, but a fluid dance between the deep Earth and the space around it, and the poles are simply markers in that grand choreography. As the poles continue their slow migration, they carry with them the quiet story of the core's ceaseless motion, a reminder that beneath our feet, the heart of the planet is always in motion, and so the map of our magnetic world will never be finished. Every so often in Earth's history, the magnetic poles do more than wander, they swap places entirely. These events, called geomagnetic reversals, are among the most dramatic transformations in the life of the shield. North becomes south, south becomes north, and the entire global magnetic field reorganizes itself into a new orientation. From the geological record, we know these reversals are not rare on a planetary timescale. The seafloor holds the clearest evidence. As molten rock emerges from mid-ocean ridges and cools, iron-rich minerals align with the current magnetic field. Over millions of years, this process has created symmetrical stripes of alternating polarity on either side of the ridges, a barcode of Earth's magnetic history. These patterns reveal that reversals have occurred hundreds of times in the last few 100 million years, with intervals ranging from less than 100,000 years to several million years apart. A reversal does not happen overnight. It begins with a weakening of the overall field strength, often accompanied by complex, shifting patterns of magnetism. Multiple north and south poles may exist at the same time, scattered unpredictably across the globe. Over thousands of years, the field gradually stabilizes into its new reversed configuration. For life on Earth, past reversals do not seem to have triggered mass extinctions. Our atmosphere continues to shield the surface from most harmful radiation even when the magnetic field is weak. But a reduced shield could expose the upper atmosphere to greater erosion from the solar wind, and during the reversal itself, satellites and electrical systems, had they existed, would have faced far more frequent radiation hazards. In the modern world, a reversal would present technological challenges. The shifting field could disrupt navigation systems, affect satellites, and require constant recalibration of the world magnetic model. High-latitude regions might see auroras more often, while low-latitude regions could experience them for the first time in recorded history. The last full reversal, known as the Bruns-Machiyama reversal, occurred about 780,000 years ago. Since then, the field has experienced shorter-lived, incomplete reversals called excursions, brief flips that return to the original orientation. Whether we are now heading toward another full reversal is unknown, though the recent weakening in some areas, like the South Atlantic anomaly, keeps the question alive. If it does happen, the planet will adapt as it always has. The shield will reconfigure, the poles will settle into their new positions, and life will continue under a sky still guarded by Earth's deep, molten heart. The reversal is not the end of the shield's story. It is simply another chapter in its long, restless history. Not every disturbance in Earth's magnetic field leads to a full reversal. Sometimes, the poles begin to wander toward a complete swap, only for the process to falter, leaving the field to snap back into its original orientation. These fleeting events are called geomagnetic excursions, and they are like half-forgotten rehearsals for a performance that never reaches its finale. Excursions can last a few hundred to a few thousand years, and during that time, the field can weaken dramatically, sometimes to a fraction of its normal strength. Like full reversals, they can produce temporary multiple poles scattered across the planet, with the familiar north and south replaced by a patchwork of shifting magnetic spots. For a compass in such a time, north might change direction not in decades, but in years, perhaps even in months. One of the most studied excursions is the Loschamp event, which occurred about 41,000 years ago. For roughly 1,000 years, the magnetic field was in disarray, and for a brief period, only a few centuries, it was reversed entirely. Evidence from ancient lava flows, ocean sediments, and ice cores shows that during the Loschamp, the field's strength dropped to less than 10% of today's level. Cosmic rays poured into the upper atmosphere, increasing levels of certain isotopes like beryllium-10, which scientists can still detect in ice from that time. For early humans and other life, the Loschamp was likely not catastrophic. Our thick atmosphere still absorbed most harmful radiation, and any effects may have been subtle. A slightly higher dose of radiation at the surface, perhaps some changes in climate from shifts in atmospheric chemistry. But for the magnetic field itself, the event was a moment of profound instability, a glimpse into how easily the shield structure can be reshaped by the restless flows of the outer core. Excursions remind us that the geodynamo is sensitive to changes deep below our feet. Even without a full reversal, the balance of molten iron currents can tip far enough to send the poles wandering wildly before order is restored. From a scientific standpoint, they are invaluable windows into the dynamics of the core, offering snapshots of the processes that lead to, and sometimes halt, complete flips. If one were to happen today, we might see an increase in auroras across much of the globe, as more charged particles slipped through the weakened shield. Satellites would face more frequent malfunctions, and power grids might need additional safeguards. Yet, as in the past, the shield would likely recover, snapping back to its familiar configuration and leaving only subtle traces in rock, ice, and the isotopes drifting in the atmosphere. In the grand sweep of Earth's magnetic history, excursions are reminders that even when the shield seems steady, it lives in a state of perpetual negotiation. never entirely still, never entirely certain, but always returning, in time, to the shape that has sheltered life for billions of years. The magnetic field itself is invisible, but the story of its past is written into stone, sediment, and ice. By reading these natural archives, scientists can reconstruct the shield's history over millions of years, tracing its reversals, excursions, and subtle changes in strength. This science, paleomagnetism, is our key to understanding the restless nature of the geodynamo. The most striking record lies on the ocean floor. Along the mid-ocean ridges, molten rock continually wells up from beneath the crust, cools, and hardens into new seafloor. As it cools, tiny crystals of magnetite within the basalt align with the direction of Earth's magnetic field at that moment. Once locked in place, these crystals preserve a permanent record of the field's polarity. Over millions of years, the steady creation of new crust has built symmetrical stripes of alternating magnetic orientation on either side of the ridges, like the barcode of a planet's deep history. On land, ancient lava flows tell similar stories. When molten rock erupts from a volcano and then solidifies, the iron-rich minerals inside act like countless frozen compass needles, preserving the direction and inclination of the magnetic field. By dating these rocks with radiometric methods, scientists can pinpoint when the field was aligned north-south or reversed. Sediments provide a more continuous record. As fine particles settle on the ocean floor or in lakes, they often contain tiny magnetic grains that slowly align with the prevailing field before becoming locked into place. These layers can be read like pages in a book, revealing gradual changes in strength and direction over thousands to millions of years. Even ice cores hold magnetic clues, though not in the form of minerals. Instead, they contain chemical fingerprints of cosmic ray activity. When the magnetic field weakens, more cosmic rays reach the atmosphere, producing isotopes such as beryllium-10 and carbon-14. Higher concentrations of these isotopes in ice or tree rings correspond to times of reduced magnetic protection, often during excursions or reversals. Piecing together these diverse records allows scientists to build a detailed timeline of the shield's behavior, one that stretches back far beyond the limits of written history. We can see the average intervals between reversals, the varying strength of the field, and how local features like the South Atlantic anomaly may have analogs in the distant past. This knowledge is not just academic. Understanding how the field has changed before helps us anticipate how it might change again. By studying its history, we learn the rhythms of the geodynamo, the pace of its fluctuations, and the warning signs of instability. In this way, rocks, sediments, and ice become more than just relics of ancient times. They are messengers from the deep earth, carrying news from ages when no human eye had yet looked up at the sky. Trying to foresee the future of Earth's magnetic field is like listening to the deep, slow heartbeat of the planet and guessing its next rhythm. We know the shield is constantly in motion, poles wandering, strength waxing and waning, but the exact timing of its next major shift remains a mystery locked in the restless currents of the molten outer core. Scientists approach this puzzle by combining three powerful tools: precise modern measurements, detailed maps of past behavior, and computer simulations of the geodynamo. The satellite era has given us an unprecedented view of the shield's present state. Observations from missions like ESA's Swarm constellation track subtle changes in strength and direction across the globe, revealing patterns of drift and regions of weakness, such as the South Atlantic anomaly. When these short-term trends are compared with the geological record of reversals and excursions, scientists can identify similarities. Moments when the field behaved in comparable ways before. But the field's history also shows great variability. Sometimes a weakening leads to a reversal, and sometimes it recovers without flipping at all. This unpredictability makes forecasting more like reading shifting weather patterns than following a fixed clock. Computer models add another layer of insight. By simulating the churning motion of liquid iron in the core, researchers can watch virtual magnetic fields evolve over centuries or millennia. These models reproduce wandering poles, occasional reversals, and the creation of anomalies. Yet they also reveal how sensitive the field is to small changes in flow patterns. Slight differences in core dynamics can send the poles racing across the globe, or leave them nearly stationary. At present, measurements show that the overall strength of the field has been declining slowly for the past 2 centuries, with the fastest weakening concentrated in the South Atlantic region. Whether this trend signals an approaching reversal or is simply part of a long-term fluctuation remains uncertain. Historical data tell us that similar declines have occurred before without leading to a flip. In practical terms, predicting the field's future is about probabilities, not certainties. Scientists can say that a reversal is unlikely to happen in the next few decades, but impossible to rule out in the next few thousand years. They can also warn of regions where weakening might pose technological risks sooner, guiding engineers to protect satellites, power grids, and communication systems. For most life on Earth, even a significant weakening of the shield would not be an immediate threat. Our atmosphere remains a formidable protector. But for the intricate web of technology that now orbits our planet and crisscrosses its surface, understanding the shield's moods is vital. So we watch, we map, we model. Each data point, each simulation, each reading from a satellite's magnetometer is another note in the long, low song of the Earth's core. And in that song, somewhere, may lie the first hints of the shield's next great transformation. To imagine Earth without its magnetic shield is to strip away an invisible but vital layer of protection. The shield is not something we see in daily life. There is no wall in the sky, no shimmer across the horizon. But without it, the planet would be exposed to the full force of the solar wind, a constant stream of charged particles rushing outward from the sun at hundreds of kilometers per second. On worlds without such a shield, like Mars, the consequences are stark. Billions of years ago, Mars may have had a magnetic field, generated by a molten core much like Earth's. But as the smaller planet cooled, its internal dynamo slowed and eventually stopped. Without the magnetic barrier to deflect the solar wind, Mars's atmosphere began to erode. Over millions of years, much of it was stripped away, carried off into space. The air thinned, surface pressure dropped, and liquid water, once flowing freely, vanished from the landscape. If Earth's shield were to vanish, the effects would not be immediate extinction, but the slow wearing down of our atmospheric defenses. The upper layers of air would be most vulnerable, gradually eroded by the relentless wind from the sun. High-energy particles would bombard the atmosphere more frequently, altering its chemistry and perhaps reducing the ozone layer that protects life from harmful ultraviolet light. The surface itself would feel the change more subtly. Radiation levels would rise, particularly at higher altitudes and near the poles. Astronauts in orbit would face greater risks, and flights over polar routes might require rerouting to avoid increased exposure. Sensitive technologies, satellites, power grids, long-distance communications would be more prone to disruption as charged particles streamed in unimpeded. Life, however, is resilient. The oceans would still shield marine life from much of the radiation, and even on land, many species could adapt or find shelter. But over geological timescales, the slow erosion of the atmosphere could alter climate, water distribution, and the habitability of the planet's surface. It's important to remember that Earth's magnetic field has weakened, shifted, and reversed many times before without vanishing entirely. The geodynamo in our core is powered by the planet's internal heat, and as long as that heat continues to drive the swirling motion of molten iron, the shield will endure. A complete loss of the field is not something scientists expect for billions of years, likely not until the core cools far beyond its current state. Yet thinking about a shieldless Earth helps us appreciate what we have now. A planet not just in the right place with the right atmosphere, but also with a living heart that stirs the molten metal beneath our feet into a force field that has guarded life for billions of years. The shield is part of the quiet miracle of habitability, as essential as air, water, and warmth, though far less visible. Most of the time, Earth's magnetic field works in silence, deflecting solar wind particles high above the atmosphere where no one can see. But every so often, the shield paints the sky with light. These are the auroras, dancing curtains of green, red, and violet that ripple across the night in the polar regions, born from the same interactions that make the shield so essential. The process begins 150 million kilometers away, on the surface of the sun. When solar activity intensifies, storms erupt, sending bursts of charged particles hurtling through space. If one of these bursts intersects Earth, the magnetic field takes the first impact. The solar wind compresses the sunward side of the field and stretches the night side into a long magnetic tail. Some particles become trapped, spiraling along magnetic field lines toward the poles. As they plunge into the upper atmosphere, they collide with atoms and molecules of oxygen and nitrogen. These collisions transfer energy, which the atmospheric particles release as light. Oxygen glows green and red. Nitrogen shines in shades of blue and purple. The result is a living tapestry of light, shimmering and folding in ways that seem almost organic. Auroras are not only beautiful, they are a sign that the shield is doing its work. Without the magnetic field to funnel charged particles toward the poles, the entire planet could be bathed in radiation. Instead, the shield channels the energy into narrow bands near the polar circles, far from most of Earth's surface life. In the far north, the aurora borealis has inspired countless myths. Celestial foxes sweeping their tails across the sky, spirits of ancestors dancing, warriors clashing in the heavens. In the south, the aurora australis weaves its light over Antarctica and the Southern Ocean, visible only to the few who venture there. For scientists, these lights are also a diagnostic tool, a way to see how space weather interacts with the magnetosphere in real time. Sometimes, during strong geomagnetic storms, auroras expand far beyond their usual bounds, appearing in skies where they are rarely seen. People living in temperate latitudes may look up and find the night painted green for the first time in their lives, a reminder that the sun and earth are engaged in a constant, invisible dialogue. The aurora is the shield's gift to us, the only moment when its protective power steps into the visible world. It is the poetry of the geodynamo, written in light instead of iron, telling us that the heart of the planet is alive, and that in its ceaseless motion, it not only guards us but offers beauty as well. Though Earth's magnetic field is often imagined as smooth and symmetrical, in reality it has its flaws, regions where its protective strength is weaker than average. One of the most notable of these is the South Atlantic anomaly, a vast area of reduced magnetic intensity stretching from South America into the southern Atlantic Ocean. Here, the shield thins, and charged particles from space dip closer to the atmosphere than anywhere else on Earth. The anomaly exists because the magnetic field is not perfectly aligned with the planet's rotation axis, nor is it centered precisely at Earth's core. The inner core's offset, combined with complex flows in the molten outer core, creates a lopsided field. Over the South Atlantic, this results in a dip where the radiation belts, the zones of trapped solar and cosmic particles, descend unusually low. For satellites and spacecraft passing through, the anomaly is a hazardous zone. The International Space Station encounters it regularly, and astronauts report higher levels of radiation when they cross it. Sensitive electronics can experience glitches, and some satellites have temporarily shut down systems to protect themselves while passing overhead. Instruments designed to detect cosmic rays often register spikes in particle counts here, not because the sun is more active, but because the shield's local protection is weaker. On the ground, the anomaly has little effect on daily life. The atmosphere still blocks most harmful radiation before it reaches the surface. But for the growing web of technology that circles the Earth, it is a reminder that the shield is not uniform, and that vulnerabilities exist even when the field is strong globally. Scientists keep a close watch on the anomaly, tracking how it changes over time. In recent decades, it has been slowly expanding and shifting westward. The rate of this movement, and the field's ongoing weakening in this region, has sparked discussion about whether it might be linked to a larger, long-term trend in the geodynamo. Some researchers speculate that anomalies like this could be early signs of an approaching geomagnetic reversal, though the evidence is far from conclusive. Whether or not it signals a deeper change, the South Atlantic anomaly shows us that the shield is alive in more ways than one. It is not a rigid structure but a fluid, dynamic force field shaped by the restless motion of molten metal deep beneath our feet. Like weather in the atmosphere, it has its storms, its calms, and its occasional thin spots. And even in its imperfections, it continues to guard our fragile atmosphere, a reminder that protection does not have to be flawless to be vital. High above our atmosphere, space is not empty and still. It is alive with currents of charged particles, bursts of energy, and invisible waves from the sun. This restless environment, known as space weather, can sometimes become stormy enough to affect life and technology on Earth. And in these moments, our magnetic shield steps into its most dramatic role. The sun is the primary driver of space weather. It constantly releases a stream of charged particles called the solar wind, but during periods of heightened activity, such as solar flares or coronal mass ejections, vast clouds of plasma and tangled magnetic fields are hurled into space. When one of these storms strikes Earth, the magnetic field is the first line of defense. The initial impact compresses the day side of the magnetosphere, forcing it inward, while the night side stretches far into a trailing magnetic tail. The field absorbs and redirects much of the incoming energy, channeling particles toward the poles where they can produce auroras. Without this deflection, the storm's energy would slam directly into the atmosphere and the surface. But even with the shield, powerful solar storms can cause disturbances. Rapid changes in the magnetic field can induce currents in long conductors on Earth, such as power lines and pipelines, potentially leading to blackouts or infrastructure damage. In orbit, satellites may be bombarded by energetic particles that interfere with electronics or degrade solar panels. High-frequency radio communications can be disrupted, especially near the poles, and navigation systems can lose accuracy. The most famous example of space weather's power is the Carrington event of 1859, when a massive solar storm produced auroras visible near the equator and disrupted telegraph systems worldwide. In today's technology-dependent world, an event of that magnitude could have far greater consequences. Our satellites, GPS systems, power grids, and even aviation could all be affected. Monitoring the sun and predicting space weather has therefore become an essential part of protecting modern society. Space agencies operate fleets of satellites to watch for eruptions on the sun, track solar wind conditions, and model how incoming storms will interact with Earth's magnetic field. With enough warning, operators can put satellites into safe modes, adjust flight paths, and safeguard power grids. Through all of this, the magnetic field acts as a constant partner to our preparedness, catching the brunt of each wave from the sun, shaping the storm's path, and ensuring that even during the most violent space weather, the planet's surface remains shielded. It is a reminder that while space may seem serene from afar, Earth lives within a sea of invisible forces, and our survival depends on the quiet strength of a shield we cannot see. Long before humans discovered the magnetic field with compasses and equations, countless creatures had already been reading it with effortless precision. Birds in migration, sea turtles crossing oceans, salmon returning to their spawning grounds. Many animals carry within them a natural sense for Earth's magnetic lines, using the shield not only as protection but as a map. In migratory birds, this ability is almost like an extra sense layered over sight and hearing. Studies suggest they can see the magnetic field as faint visual patterns, possibly through light-sensitive proteins in their eyes called cryptochromes. When sunlight strikes these molecules, they may react in ways influenced by the field's direction, overlaying a subtle compass in the bird's vision. This helps them maintain steady courses over thousands of kilometers, even across featureless seas or in the darkness of night. Sea turtles hatch on remote beaches, then vanish into the open ocean for years before returning to the very same stretch of sand to lay their eggs. Research shows they imprint on the magnetic signature of their birthplace, the unique combination of field strength and inclination angle at that location, and later use this signature like a home address stored in memory. Salmon navigate from the vastness of the ocean back to the streams where they were born, seemingly guided by a similar magnetic imprint. Even small creatures like lobsters and certain species of moths display magnetic orientation, suggesting this sense is deeply woven into life's fabric. The exact mechanisms differ from species to species. Some rely on magnetite, a naturally magnetic mineral found in tiny crystals within their bodies, which may physically tug on sensory cells in response to the field. Others depend more on light-based chemical reactions sensitive to magnetic influence. In some cases, both systems may work together, providing redundancy and accuracy. Humans, too, might possess a faint remnant of this ability. Experiments have hinted that certain brainwaves change in response to shifts in magnetic orientation, though most of us are no longer consciously aware of it. For our ancestors, before maps or satellites, even a weak magnetic sense could have been useful in wandering unfamiliar landscapes. This connection between life and the magnetic field is more than a curiosity. It is a reminder that the shield is not only a planetary-scale protector, but also a subtle guide woven into the evolutionary history of countless species. For them, the field is not an abstract scientific concept. It is a silent, ever-present thread that shapes the paths of their journeys. For most of human history, the magnetic field was an unseen mystery. People could feel the wind, watch the clouds, and track the sun's path across the sky. But the shield's invisible lines of force lay hidden, influencing the world in ways no one could yet measure. Its presence was revealed slowly, piece by piece, through curiosity, trade, and the long journeys of explorers. The earliest clues came from lodestones, naturally magnetized pieces of iron or that could attract small bits of metal. Ancient records from China suggest that as early as the 4th century BCE, people discovered these stones would align themselves in a consistent direction when suspended or floated in water. Over centuries, this property evolved into the magnetic compass, a tool that transformed navigation. By the 11th century, sailors in the Song dynasty were using compasses to guide their ships, even on cloudy days or dark nights when the stars were hidden. As trade routes expanded, the compass spread across the world, first to the Arab world, then to Europe, changing how people explored oceans and continents. Yet even as it became indispensable, the reason behind its power remained elusive. Some believed it was drawn to a magnetic mountain at the world's edge. Others thought it followed the motion of the heavens. The scientific understanding began to deepen in the 16th century, when English physician and natural philosopher William Gilbert published De Magnete. Through experiments, he concluded that the Earth itself was a giant magnet with poles and a magnetic axis. His work laid the foundation for viewing the compass not as a mystical instrument, but as a direct connection to the planet's own force. In the centuries that followed, explorers and scientists mapped the variations of the magnetic field across the globe. They noticed that the magnetic poles drifted, that declination, the difference between magnetic north and true north, varied by location, and that magnetic strength was not uniform. With the advent of modern physics in the 19th and 20th centuries, the link between the field and the molten iron core was finally understood, giving birth to the geodynamo theory. The space age brought an even more profound perspective. Satellites revealed the field's true shape, a teardrop-like magnetosphere compressed on the sun-facing side and stretched into a vast tail on the night side. We learned that this shield guards our atmosphere from solar wind erosion and cosmic radiation, and that without it, Earth's history might have been far shorter and harsher. What began as a mariner's practical tool had become a window into the planet's deep interior and its cosmic environment. The discovery of the magnetic shield is a story of patience and wonder, of centuries of small observations adding up to a revelation. That beneath our feet, a hidden dynamo turns, and above our heads, its invisible hand guards the sky. The magnetic shield is not merely a scientific curiosity. It is a thread woven through the entire tapestry of Earth's history. From the planet's fiery beginnings to the quiet nights we know today, it has shaped the conditions in which life could emerge, persist, and flourish. Without it, our skies might be thin and bare, our seas frozen, our landscapes stripped by the relentless breath of the sun. It began deep within the newborn Earth, when the planet's molten heart was restless and hot. The swirling oceans of liquid iron in the outer core birthed the geodynamo, a self-sustaining engine that would hum for billions of years. This engine created more than a field, it created a sanctuary. Within its reach, the early atmosphere had a chance to thicken instead of being blown away. Water could pool and rivers could flow. Life, fragile and tentative, could take root in a world that was otherwise hostile. Over eons, the shield has endured changes both subtle and grand. The poles have wandered. The field has weakened and strengthened. It has even flipped entirely, swapping north and south as though turning the page of a book. Yet through each shift, the shield has never abandoned the planet it protects. Even in its moments of greatest change, it has remained strong enough to keep the essentials of life safe. Its influence is not limited to protection. The shield has also been a quiet guide. Migratory birds trace its lines across continents. Sea turtles use its patterns to find their birthplace. Humans, without knowing it, have long relied on it to cross oceans and deserts. In this way, the magnetic field is both guardian and compass, its presence written into the behavior of species and the course of civilizations. Now, in our modern age, we can see it not only as a planetary phenomenon but as part of a universal pattern. Other worlds, Mars, Mercury, Jupiter, each tell their own stories about magnetic fields, and in comparing them, we better understand our own. We see how rare it is for a planet to have a shield like ours, and how fortunate we are to live under its watch. In the end, the magnetic field is a reminder that Earth is not static. It is alive in ways we cannot see, breathing in cycles of molten iron, pulsing with invisible energy, conversing silently with the sun. The shield's place in Earth's story is not a single chapter. It is the constant margin around every page, the border that has allowed the narrative of life to be written at all. And so, as we look up at the stars, knowing the vastness of space and the forces that move through it, we can be grateful for this unseen companion. For as long as the heart of our planet beats, the shield will turn with it, a patient guardian, holding back the darkness so that life can dream beneath the stars.